alkaline earth because earth is related to their hydroxides, and since the hydroxides are alkaline in nature, so we all know that the group 2 elements, they are called as alkaline earth metals, and they comprises this group 2. It comprises of elements like beryllium, magnesium, calcium, strontium, barium, and radium. And their electronic configuration, the outermost electronic configuration here it is given, as you can see. So however, we will also have in the following section, we will also have a discussion on the properties of group 1 and group 2 metals in details. Now, coming to introduce the transition elements, they lie between the S group and the P block elements. So that is why they have been termed as transition elements. And here, this in the periodic table, here it is in figure 1.1, you can see the position of the transition elements in the periodic table. That is group number 3 to this 12, they are the transition elements. And then within the transition elements, we have the inner transition elements, that is the group that is called as the lanthanides and actinides. These are some of the common properties that we all know till today. Now, so first we will talk about the transition series. So if we look into figure table 1.3, it shows the electronic configuration and of the free atoms and the dipositive atoms of the first transition series. So here, if we look here, we know the first transition series, it starts with scandium here, and then here some of the list elements: scandium, titanium, vanadium, chromium, manganese, and up to it continues up to 30, that is zinc. So that it comprises the first transition series, and the last electron, outermost electron, it goes into the d orbital, and that is why the transition elements, they are also called as d block elements. Now you all know this. Then here in table 1.4, the electronic configuration of the elements of the second transition series, it has been listed here, as you can see in table 1.4. Then the third transition series, which we know it consists of the elements lanthanum. And then here particularly the lanthanide elements begin, and the electron starts filling in the 5d orbital. And you can see in table 1.5 the electronic configuration of the third transition series that has been listed here. Now here, this lanthanum, after the lanthanum, then we have the inner transition series, that is referred to as the lanthanide series. And the fourth transition series of the transition elements, that is starts from actinum 89, and then it continues with the inner transition, that is the 6f elements. It goes into this fourth series. And then finally here in table 1.6, you can see the configuration of the fourth transition series. Now, these are some of the very fundamentals of inorganic chemistry that we all know. So now here we have, basically going into the details, we need to understand the SPDF orbitals and their penetration power. Now we know the extent of penetration, it follows this order: S is greater than B, is greater than D, and greater than F. Now we all know what is SP, D, and F, and also we understand what is the principal quantum number, the principal shell, and all those things. So here, if we look into figure 1.2, here we have a very important figure, that is, it is called as the radial distribution of 3d and 4s atomic orbitals, and it is given in H atom, that is qualitatively. So here, if we look into the particularly shells like 3s, 3p, 3d, we know that they have the same energy. However, this nature is not true for complex atoms. Now when we consider a very complex atoms, the ns orbitals, they penetrate most, and that is why they have a higher effective nuclear charge. So we'll gradually come to know what is effective nuclear charge, and we also know how do the filling of electrons in an orbital takes place. That is why we know here, we know why the electrons enter the 4s orbital rather than 3d orbital. In normally in after argon, in potassium and calcium, we always write the electron always enters into the 4s rather than 3d, and the nature, it is this follows the above principle, and we also know about the filling of the electrons in different orbitals. Now here, after this, if we look into, we'll start gradually look into the electrons of the potassium and calcium. So let us consider the potassium and calcium. Similarly, we can say we can also write what is the ground state electron of potassium and calcium, followed by their ionic configuration. So these are all the common things that we know. Now, if we look into the configuration of copper, now we all know copper is an element of the first transition series, which it has the following 3D8 4s2 is nickel. However, we generally speaking, copper it should follow 3D9 4s2 configuration, argon 3D9 4s2 configuration. But we know that the ground state electronic configuration of copper is 3D10 and 4s1, and we all know why this electronic configuration is followed. This is because the half filled and completely filled orbitals, they are more stable in nature. That is why, in order to provide stability to the orbitals, here copper is written as 3D10 and 4s1, right? So this is about copper. Here it is shown in electronically. Now we'll come to, so these are some of the exceptions in electronic configurations, and there are various general trends in electronic configurations, and we also have some certain exceptions. So now we'll gradually come to the periodic trends in properties. So in there are various properties that is related to an atom, and then they are the, according to their placement in the periodic table, they follow certain trends. So first we will start with the atomic radii. Now, as the name implies, atomic radii, it measures the size of the atoms. So these are very important properties because they are related, these atomic radii, it is related to other physical properties, other properties like ionization, enthalpy, the electronegativity, the electron affinity. So there are various factors that are directly dependent on atomic radii. So now, when we consider the radii of an atom or a molecule, they have been atomic radii. They are broadly classified into four types. One is the covalent radius. Second is what we call it as the metallic radius. The third is the van der Waals radius, and the fourth is the ionic radius. So depending upon the type of the bonding that occurs between the atoms that we have considered, so accordingly atomic radii has been divided into these four mentioned classes. So now coming to what is a covalent radius. A covalent radius, it is defined as half of the internuclear distance between the two atoms in a covalent molecule. That is, suppose if we consider a homonuclear diatomic molecule such as F2Cl2, these are homonuclear diatomic molecule, and their internuclear distance is given that as Ra. So to this Ra, or the covalent radius, is equal to half of the bond distance between the two atoms. That is, here it is given Ra is equal to half of R and the bond length between the two atoms. So even if this is for a calculation of covalent radius in a homonuclear diatomic molecule. Now, if we consider a heteronuclear diatomic molecule of the type AB, then the bond length, here it is Rab, and the total and the covalent radii is given as Ra plus Rb, which means it is the sum of the covalent radii of the atom A and atom B. So this is how we calculate for a heteronuclear diatomic molecule. Now, suppose if there is a difference in electronegativity between the two bonded atoms, let us consider two atoms A and B, but they have different electronegativities. So there, in that case, Shoemaker and Stevenson, they have proposed a different type of relationship, and the RAB is calculated using this formula. This is equal to the covalent radii of A plus covalent radii of B minus 0.07 into chi of A minus chi of B whole square, where chi A and chi B, it represents the electronegativity of the A atom and B atom. We'll gradually come to electronegativity, but this is used for hetero nuclear diatomic molecule having different electronegativities. Now here in table 1.7, various covalent and van der Waals radii of different elements have been listed. Mostly you can find it that covalent radius is in pm and van der Waals radius is also in pm. Per pm it indicates picometer. Mostly, most of the radii that we will come across, they have this, the unit is pm. So now we'll start with here, coming to here is an equation that is solved, uh, is a question for you that you will solve now. Okay, now coming to figure 1.3. So here you in figure 1.3 you can find see the covalent and van der Waals radii of solid chlorine. So here we know the calculation of covalent radius and van der Waals radius has been illustrated in this figure. So how exactly we calculate the covalent radii and the van der Waals radii? So here now we will come another type of radius that is called as the metallic radius. Now metallic radius, as the name it implies, it is defined as the half of the internuclear distance between two adjacent atoms that are present in a crystal lattice. So for example, the internuclear distance between two adjacent atoms in a sodium lattice is 383 pm. So therefore, the radius of the metallic radius for sodium atom will be half of 383, and this comes to 191 pm. So this is how we calculate the metallic radii, and this is mostly it is done for a crystal, metallic crystal. We calculate the half of the internuclear distance between the two adjacent metal atoms in the crystal, so in the lattice. So then comes the ionic radius. The ionic radius, it is defined as the distance between the nucleus of an ion and the point up to which the nucleus influences the electron cloud. Now, in particularly in ionic radius, we consider the nucleus of the ion. That is, we'll consider the distance of the ion to the point of where on the other atom where it has an impact on the electron cloud. Now we all know that all common cations, they are smaller than all common anions except for rubidium and cesium, so which are largest, and fluoride atoms, they are the single smallest atoms that we have known. So here we can know that thus when we consider a isoelectronic species such as N3 minus, O2 minus, Na plus, here all the examples are given. The greater is the effective nuclear charge, the smaller is the radius of the species. That is, in general, we can say that there is a decrease in anion size from the anions to the covalent radii of the corresponding atoms to cation. This is how we calculate. So particularly for an isoelectronic species, the more is the nuclear charge, effective nuclear charge, then the smaller is the size of the species. So here in table 1.8, various metallic and ionic radius of elements that have been listed for group 1 to group 18 elements, as you can see here. Now in comparison, we'll compare that the size of alkali metals. We know that the alkali metals, they are the largest in their corresponding periods in the periodic table. Suppose we consider a particular period, then we know that the alkali metals, they have the largest size in comparison to other metals present in the corresponding period. So the size of the atom or its ion, it increases, that we know on descending the group. So as we go down the group, the size of the atomic radii or the ionic radii, it both increases as we go down the group. Now this happens because the extra electrons, that when we add an extra electron, it goes to the addition of an extra electron, it outweighs the effect of the increased nuclear charge, and thus there is an increase in size from lithium to cesium. So when we look into group 1 particularly and we go downwards, then we see that the size increases from lithium to cesium, and this also is because of the addition of one more cell with the going down the group. So now even the atoms of the alkaline earth metals, they are smaller than that of the corresponding group 1 elements. We all know that as we go across a period, the size decreases. So when we compare the sizes of a alkali metal and that of an alkaline earth metal, we know that the ionic atomic radii and the ionic radii of the elements of group 2, they are smaller than those of the corresponding group 1 elements. Now this is particularly because of the increase in effective nuclear charge with increase in atomic number. Now as the effective nuclear charge increases, the valence shell electrons, they are more attracted towards the nucleus, so thus the size of the atoms are decreases. So similarly, the ionic radii for group 2 elements, they are also smaller for than that of group 1 elements. So these are the general observations. Now here the trend in the variation of the metallic radii in alkaline earth and alkaline earth metals and transition metals, they have been given in here, table 1.8. Here it is shown, and the figure they have been schematically shown in figure. The variation has been shown in figure 1.4. So if you look into figure 1.4, it shows how the variation of the with metallic radii with group number. Here you can see in figure 1.4. So from this figure we see that as we move from alkali metals to alkaline earth metals and from alkaline earth metals towards the transition series, the radii decreases steeply. But however, when we look into the decrease in the transition elements, then the rate of decrease of atomic radii or the metallic radii in the transition element series is gradual, it is very less. So this is because of the increase in inter-electronic repulsion after the addition of sufficient number of electrons that actually goes into the d orbitals due to the gradual increase in size. So there is a very important observation from this graph. So the transition metal series, that the decrease, although a decrease in the atomic radii and ionic radii occurs, however, the decrease is very gradual in the transition series in compared to group 1 and group 2. So now there are various factors that influence the atomic radii. So we shall first discuss two of the major factors which influence the atomic radii. The first is called the principal quantum number, that is the n. So here n plays a very important role in deciding the atomic radii of a particular element. So now we know that as the n increases, that is as we increase the principal quantum number, so the outermost electron, it gets farther away from the nucleus. The internuclear distance, that is the distance from the outermost electron from the nucleus, is more as n is increased, and hence the atomic radii generally increases with the increase in principal quantum number. Now the second factor that affects the atomic radii is the effective nuclear charge. This effective nuclear charge is represented as Z star. So the magnitude of the effective nuclear charge, it effectively determines the magnitude of the force of attraction that is exerted by the nucleus on the outermost electrons. So when the magnitude of the Z star is more, then the force uh, that is influenced on the outermost electrons is more. So hence the electron cloud of the outermost electron is pulled inward. As the nuclear charge increases, the electron cloud is pulled inwards towards the nucleus, and consequently what happens is the atomic radii decreases. So first we'll define what is this effective nuclear charge. So in general, the effective nuclear charge or Z star is defined as the amount of positive charge that is felt by the outer electrons in an atom. So it is always less than the actual charge, which we represent as Z of the nucleus on the atom. The effective nuclear charge, it is actually the charge which is felt by an outer electron, and it is dependent on the actual nuclear charge and the number and type of the electrons. Those are called as the screening electrons that is present between the nucleus and the outermost shell. So here it is given as, mathematically we write Z star is equal to Z minus S, where Z star, it is the effective nuclear charge, and here the S is called as the screening constant or the shielding constant. Now this, the calculation of shielding constant or the screening constant is done with the help of Slater's rule, by applying certain rules. So these are called as Slater rules. So for the determination of S, we first need to write down the electronic configuration of the element that is under consideration. So once we write the electronic configuration and we put in proper order of the electronic configuration, that is, in, we cannot just write randomly, so we have to write in proper order that has that follows the general rules of the writing of the electronic configuration. Now we see then that particular electron in particular orbitals, they have a particular value. So here you can see in point 3 that all other electrons in the ns and np ground group, they contribute S is equal to 0.35 each, except for the electron in 1s which contribute to S is equal to 0.30. Then again we see that all electrons that are present in the n minus 1 shell, they contribute S is equal to 0.85 each. And finally, all the electrons that are present in n minus 2 or lower than that, they contribute to S is equal to 1 for each. So again, if we look for an electron that is present in a Nd or a Nf orbital, so here all the electrons, that is Nd or Nf, they contribute S is equal to 0.535 for each electron. And similarly, those in the groups lying lower in the sequence than the Nd or Nf, they contribute S is equal to 1 each. So here we have to remember the contribution values, that is S for each of the Ns, Np, Nd or Nf orbitals, and then substituting these values at the particular electronic configuration, we can find out the screening constant. So here, for example, an example has been shown for the calculation of Z star for an electron in potassium and zinc. So we will consider the case of potassium. So the electronic configuration of potassium, here it is given as 1s2, 2s2. So first we will write the ground state electronic configuration for potassium. So here it is written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So now we will, the grouping of the orbitals will be done. So what is, we will now group the ns, np, nd, nf orbitals here accordingly. So accordingly to the values of n, the orbitals have been grouped. Now we will substitute from the Slater's rule the particular values of the screening constant. So accordingly, we look into the electrons and we find out that the value of S for the electron here in the 4s orbital is given as 16.8. So we need to substitute the values, the screening constant values, and from this we find S to be this. Therefore, the effective nuclear charge for potassium, that is Z star, we know it is given as Z minus S, and the Z for potassium is 19. The S that has been calculated here is 16.8. Therefore, the effective nuclear charge for potassium can be written as Z star is equal to 19 minus this and 2.2. So that this is how we calculate the effective nuclear charge from Slater's rule. Another example here, it has been shown here for zinc, and similarly the other for other atoms or other elements, Z star can be calculated. So here in table 1.9, the effective nuclear charge for the first 30 elements have been listed here. So here you can look into this table. The Z, the screening constant value, and the Z star value has been found out and it has been listed here. So now coming to a periodicity in atomic radii. So periodicity means, so we know that there are two factors particularly which influences the atomic radii. One is the principal quantum number and another is the effective nuclear charge. So now here we'll look into the periodicity of the atomic radii. Now two general periodic trends are found for all the four types of atomic radii. So what are the general periodic trends? These are that the atomic radii, it decreases along a period and it generally increases down the group in a periodic table. So we all know this, that the atomic radii, it increases down the group and it decreases along a period. Now these changes in effective nuclear charge, that is the Z star, and principal quantum number play an important role in deciding this periodicity. Now here, as it is shown in in table 1.9, we see there is a steady increase in the value of Z star. Here when we look into table 1.9, just a minute. Here, if we look into table 1.9, it shows that the value, there is a steady increase of almost 0.65 units in the value of Z star as we move along the periods for element 2 and 3. But there is no change in the value of n, because n remains constant, because the electrons, they go into the same n cell. So as a result, there is a steady decrease in the covalent radius. And we know, because here as the Z star, that is the effective nuclear charge, it increases along the period, while the n remains constant, that is the principal quantum number, it remains the constant. Therefore, as we move along a period, the size, the atomic radii, it decreases. Similarly, in comparison to above, the decrease in covalent radii across a transition series is much smaller. This we had already seen, that when we look into the decrease in the atomic radii or the covalent radii of transition element series, the decrease is not much marked. Although the decrease occurs, but there is a gradual decrease. There is a very small increase in effective nuclear charge of only 0.15 units. However, here we see an increase of 0.65 units, but along a transition series, the effective nuclear charge increases at a very low unit of 0.15. Therefore, only a small decrease in atomic radius from one element to another take place. So across the 10 elements of the first transition series, it has been marked that an overall decrease of 19 pm is marked between the starting and the last element of the first transition series. So we can see that the decrease in radius is very less. However, due to this, the covalent radii of the elements from Ga to Kr, it become much smaller than that is actually it should be. The decrease is so small, however, because of this effective nuclear charge. So now coming to lanthanoid elements, we know that lanthanoid elements or the lanthanoid series, they are called as the 5f series. So here the filling of the n-2f orbital takes place, and simultaneously there is a nuclear charge increase in the n nuclear charge. So the electron that are present in the n-2f orbitals, they determine the size from which increase in nuclear charge is almost around s is equal to 1. So because of this, there is a very small decrease in the atomic radius from one element to another. Now we know that in this lanthanum series, there is a total of 14 elements, and the contraction is much less is occurred, or a contraction of almost 13 pm, that is very less is occurred, and this is what is called as the lanthanoid contraction. So following which, we know there are various consequences of lanthanide contraction. So because of which lanthanide contraction, it almost cancels out the effect of the last shell added in the sixth period, and therefore the transition elements of the 5D and 4D and 5D series, they have the same atomic radii. Now similar to lanthanoid contraction, we also have actinoid contraction. So however, the actinoid contraction is not much pronounced, and therefore we do not see, although the radius change is not much marked, the elements that are present in the 5D series, they have the consequences of this actinoid contraction. Now when we look into, go down the any group, in the periodic table, the number of electrons that are present in the valence shell, it remains the constant. That is the number, but the number of shells, that is the principal quantum number, it increases. So the effective nuclear charge, it is felt, that is felt by the valence electrons, it's nearly the same. So with the increase in the n value of the valence shell, and the increase in atomic radii is generally observed. So this increase in the atomic radii of alkali and alkaline earth metals as we go down the group is well known. However, with the inclusion of 3D elements in period 4, the increase of radii in the elements of gallium to bromine is smaller than accepted. So there are, although we have certain trends, we know that the atomic radii, it decreases along a period and it increases down the group. We do encounter a few exceptions to this case, such as like increase in the radii of element from gallium to Br is much smaller than it should be. Now here in figure 1.6, the it shows the variation of the radius of M2 plus ions for 6 coordinate complexes of the transition metals 3D series. Now these are the low spin complexes that has been shown here. So here we can see what happens to the ionic radii, the decrease and increase. And at D5, if we look into D5, the value of the ionic radius, it gives value for which the increase in Z star. So there are the various, owing to the different types of pairing in the possibilities that we know that transition elements, they have various oxidation states, variable oxidation states, and the pairing occurs in many ways. So therefore here, particularly in figure 1.6, it shows how the ionic radii of particularly M2 plus ions only, they vary within the transition series. Now coming to another property that is called as atomic volume and density. These are two general trends that are observed in the like densities of the elements. So here we know that along a period there is a general increase in the density. So if we go along a period, the density increases because the atomic mass, because there is the atomic mass is increased and the size of the atom decreases. So therefore in a particular period, the alkali metals, they have the lowest density, because as we move along the period, the density increases. So here from table 11 point from table here it is 11.1. So there it has been from table 1.1, the various properties has been listed and you can see this. And so we know that the size of an atom is also related to its atomic volume. So what happens is, as the size is directly related to atomic volume, the trends also follow the same way. So across the period, as the size it decreases, the density is high. So thus there is a general trend for increasing density across the elements of a transition series. Now we know since here in transition series the size decreases, so as a result of this the atomic density is high, and which further we can mark it from the, that is figure here it is represented in figure 1.7. It shows the various trends in the densities of the alkaline earth metal and the transition metals. That shows how an atomic, they have, it varies with corresponding group number. So on descending one of the main groups of the elements in the S and P blocks, we know as we go down, the size of the atoms, it increases because the principal quantum number n, it is increased. So the elements that are present in the first group in the D block, they show the expected increase in size, but when we go into the subsequent groups, there is an increase in radius between the first and second, but there is a very little increase between the second and third. This trend is actually shown for both covalent radii and ionic radii, and between lanthanum and hafnium there are 14 lanthanoid elements present, so where the penultimate shell of electrons is filled, and that is where they have, we have to look into the, so they do not actually, they are not kind of, they do not follow a proper density, atomic density trend. So the atomic volumes of the transition elements, they are low as compared with the elements in the neighboring groups 1 and 2. So here it is because the increased nuclear charge, here it faces very poor screening effect, and so the electrons, they are more attracted strongly by the nucleus. So the attraction that the electrons feels is more by the nucleus. So further, the extra electrons that have been added, they go into they occupy the inner cells. So because of this, the density of the transition elements are high, and they are mostly greater than 5 gram per cm cube. However, the only exceptions are scandium and titanium. So they have the densities of the second row and are high, and the third row are also even higher. So here it is clearly marked in figure 1.7. So also we know that due to lanthanide contraction, we see a gradual decrease in the size of the lanthanide elements. So as a result of this, the second and third row transition elements, they have similar radii. So as a result, because of similar radii, they have also similar lattice energies, the solvation energies, and the ionization energy. So the difference in properties between the first and second row elements are much greater than that is observed between the second and third row transition series. So it is all because of the lanthanide contraction that influences the various properties on the right side of the D block. So now after this, coming to various melting and boiling points. Now we all know that alkali metals, they are quite soft in nature. Like sodium metal, it is very soft in nature, and we can just cut sodium metal with a kitchen knife. So as a result of increase in the size and repulsion of the non-bonded electrons, the cohesive energy and the tendency for metallic bonding, it decreases down the group, and thus the softness of the elements, it increases as we go down from lithium and cesium. So this is a very common property that is marked in alkali metals. So down the group, the softness increases. So as a result, they have low melting points and boiling points, so which also reflect the low values of their cohesive energy between the atoms. So in general, we can say that as we go down from lithium to cesium, the melting point and boiling point, it decreases as we go down. So on the other hand, the group 2 metals, they actually have higher melting points when compared to group 1 metals, and the reason is that they have +2 charge on their cations in their metallic lattice. So as a result, they are strongly attracted to the electrons, and that is why the intermolecular attraction being strong, and it is very difficult to pull them apart. So the melting and boiling point of the transition elements, they are generally very high. They have typically melting points above 1000 degrees centigrade. So however, there are a few exceptions, like lanthanum and silver, they are around 920 and 960 degrees centigrade. One of the notable exception is mercury, which is liquid at room temperature, and it melts at minus 38 degrees centigrade. So here these, and also we have zinc and cadmium. The melting point of zinc is 420 degrees centigrade, and that of cadmium is 321 degrees centigrade. So here we do see an exception, we do an encounter an exception in zinc, cadmium, and mercury as it is, it remains in we know it is liquid at room temperature. So here the last three elements, they behave like this because in all these cases the d shell is complete, and the d electrons, they do not actually participate in any metallic bonding. So the high melting points, they are they are in contrast to the low melting points of the S block elements. Now, typically the S block elements, they have melting points of lithium is around 181 degrees centigrade, and cesium is 29 degrees centigrade. Wherever when we see that of particular transition elements, they have melting points above 1000 degrees centigrade. So the melting points of the transition elements, it depend upon the strength of the metallic bond, which increases with the availability of the electrons. Now, if here in figure 1.2, the trends in the melting points of group 1, group 2, and the transition metals of 4th, 5th, and 6th periods, here they have been listed. So if we look into this figure 1.10, here it is given. sorry, if we look into figure 1.9, the variation of the melting point, we can see that between calcium and scandium, where the electrons first appear, there is a jump in of almost 700 degrees in the melting point. This is because of the presence of the unpaired d electron that leads to higher interatomic bonding, and therefore an increase in the melting point, the increase in the metallic bond we can see, and thus which as the strength of the metallic bond it increases, we also see a high melting and boiling point. However, these are certain anomalies that we observed in figure 1.9. So in general we can say that the melting points of transition elements are much higher than that of those S and S block elements. Now, similarly, the periodic trends in the boiling points are also similar to that observed in the melting points. So now coming to the next factor, that is ionization energy. This is a very important aspect. So this is defined as the amount of energy that is required to remove the least strongly bound electron from an isolated gaseous neutral atom in its ground state. It is known as the ionization energy, or we can say it as the ionization potential. This implies here M, that is present in gaseous state, the amount of energy that is required to remove the electron, that is to form a cation, to form M plus G plus the amount of energy that is liberated here. So since more than one electron is possible to be removed from an atom, the energy that removes the first an electron from the outermost shell is called as the first ionization energy. Similarly, successive ionization energies are also possible. So these are like second IP or second ionization energy or the third ionization energy. So the second ionization energy, it forms M2 plus, and successive ionization energies are formed. Now the ionization energy that is given here as I of an outer valence electron, it is related to the effective nuclear charge felt by the electron and its average distance from the nucleus. It is given by this equation. So I is equal to Z star into E square by 2 into 1 by R. So, or 1 by R average. Here, Z star is the effective nuclear charge, E is the charge on the electron, and 1 by R average. Here, it represents the average value of R 1 by R, where R denotes the internuclear, that is the distance of the electron from the nucleus. So, this is the general equation that has been used. Thus, when we see that the higher is the effective nuclear charge that is felt by the electron, higher will be the IE, that is the farther the electron from the nucleus, so the lower will be the ionization energy, and hence it will be vice versa. So the valence shell electron of particularly noble gases, they are exceptionally stable, and therefore their IE are highest in their respective periods. So as we know that since they have a stable configuration, their IE remains very high. So here table 1.10, it shows the various ionization energies of different types of elements. Now, group 1 elements, they acquire the electronic configuration of the preceding noble gas elements. So they have a high tendency to give up since they have NS1, the outermost electronic configuration is given as NS1, they have a high tendency of giving up the single outermost electron to form a univalent cation. So therefore, their first ionization energies are the lowest in the respective periods. Now, as we go down the group, their atomic sizes increases, thus, and their ionization energy decreases, and which results in an increase in their reactivity. So therefore, what happens here, possibility is, particularly in the case of Li plus, Na plus, K plus, they have stable electronic configuration, the Li plus, Na plus, and thus the removal of a second electron from them is very difficult, and hence these elements, they form univalent cations only. So the first ionization energy of different elements have been listed of the particularly of the alkaline earth metals. Here they have been listed in table 1.2. Now the alkaline earth metals,
कौन
they have,
क्लास से
hello,
हेलो हेलो
hello,
Hello, ma'am. I want to ask
Huh?
something.
Let me just finish this IE. We'll have a discussion at the end of this class.
Okay, ma'am.
Okay. So here the alkaline earth metals, they have higher effective nuclear charge and they are smaller in size, and therefore they are more tightly bound to the nucleus. So the second ionization energy of these elements is very high. The first ionization energy, that is the removal of the first electron, and the second of these electrons, since they have ns2 configuration, so the second ionization energy is much high, is almost twice their first ionization energy, because the second electron goes it more closely to the nucleus. So what happens, but their second ionization energy is much less than that of the corresponding alkali metals. So the ionization energy of earth metals also it decreases on moving down the group. So here in figure 1.10, we see a variation of ionization energy with atomic number. So this is about ionization energy and the other factors that have been pointed out here. So now looking into the trends in ionization energy down the group. So we already know that on moving down the group, so of s and p block elements in the periodic table, the effective nuclear charge it remains constant, but there is an increase in the principal quantum number, that is n. So the predominant factor in determining the ionization energy is the atomic radius rather than the z star. So therefore the ionization energies decreases down the group in the case of the main group elements in periodic table. However, when we go for a transition elements, opposite trends are observed. Like the first ionization energy corresponding to that of 3D and 4D series, they are almost similar, but they are much smaller than the first ionization energies of 5D series. So certainly, so these values of higher values of the energy of 5D transition series, this is in accordance with the small size of their atoms. So then coming to the different trends in successive ionization energy. So successive ionization energy, that implies the second, third, fourth and other ionization energy. And here in table 1.11, the successive ionization energies, they have been listed here. Now from this table, we know we can find out that the successive ionization energies of this element, they inevitably become larger, because the removal of the successive electrons it needs more energy. So it is also clear from table 1.1 that the difference between the successive ionization energy of the same element, it is not constant. So whenever there is a change in the value of n, we can see the change in the ionization potential for both the for a particular element. Like for example, for alkali metals, the second ionization energy, they are much higher than that the first. And for alkaline earth metals, the third ionization energies are much larger than the second. So these, particularly these such differences, they cannot be just explained on the basis of the value of z star or n. We need to also consider other factors such as their electronic configuration, their stability, their and other factors, pairing energy, and all these factors. So then coming to another property, that is periodic trend we will discuss, and it is electronegativity. So electronegativity means the tendency of attracting the electron, the share of the shared electron pair towards itself by a particular atom in a molecule is called as electronegativity. Now it cannot be measured directly. This concept of electronegativity, it was first developed by Pauling. Now he defined it on the basis of thermochemical data. So here we will consider EAA, that is the energy of AA, and BB, they are two homonuclear atoms, the bonds. So the electronegativity, the electros here it is given by this factor. So where Chi A and chi B, they designate the electronegativity of the element A and B respectively. Now, to simplify this equation has been further simplified and it has been given by this formula. However, this formula, it just gives the difference in electronegativity, that is delta chi of AB, but it does not indicate the absolute electronegative value for a particular element A or B. We can just find out the difference for AB molecule using this formula. So, in order to modify the above the concept of electronegativity, Mulliken he defined electronegativity as the mean of the IP, that is ionization potential, the first ionization potential, and the first electron affinity. So here the Mulliken's formula for the calculation of electronegativity of an atom A is given as chi A is equal to I, that is the first ionization energy of the element A, plus the electron affinity of the atom A whole divided by 2. So according to this relationship, a very electronegative element, it has also a very high ionization enthalpy. So according to Mulliken's, the electronegativity values on the Mulliken scale, they are about 2.8 times those of the Pauling's values. And the further the trends in the variation, they also are also not the same. So here in table 1.2, the electronegativity values of different elements have been listed here. Now, after this, after the Mulliken scale, one of the most commonly accepted scale has been the Allred and Rachau scale. So, where the electronegativity is equated to the force of attraction between an atom and an electron that is separated by a distance equal to the covalent radius of the atom. That is, according to this scale, here the chi of an atom A is given by the formula 3590 Z star by R square plus 0.744. So here the Z star versus R square, it gives an approximately straight line, and this method is actually, it has an advantage in the sense that it can be applied to a comparatively large number of elements. And here in table 1.2, the values that have been present here, the electronegativity values that has been present in Pauling scale and the Allred-Rachau scale. So, and they are also almost comparable values. So the all the electronegativity scales, they give average values of electronegativity, and the in general we say that the larger the difference between the two electronegativities between the two elements, then the more polar the bond will be between these two elements. Yes. Yes, go ahead. Okay, so now we'll talk about periodicity in electronegativity. So electronegativity values, the trend is almost similar to that of the ionization energies. So as the electronegativity, it increases sharply across S and P block elements because the effective nuclear charge it increases. Suppose considering from lithium to fluorine, so the electronegativity increases. However, the increase across the transition element series, the increase is much smaller because the addition of the extra electron, it is being added to the inner d shell, which provides good shielding for the outer electron from the nucleus. Although we see an increase in electronegativity, but the change is much smaller. Here transition elements, they have very low values of electronegativity. It increases from scandium to copper, and but this increase is much slower as compared to the additional electron. So coming to electrode potential, this is also one periodic property. So when we know that a metal is placed in a solution of its ion, a potential difference is set up between the metal and the solution. So the value of this potential difference, that is measured in volt, it depends upon the type of the metal that is used and the concentration of the metal that is taken in solution, plus the temperature with which, that is the working temperature. So in general, the potential difference in a 1 molar solution of metal ions at 298 K, it is referred to its standard electrode potential, and we write it as E0. So measuring the standard electrode potential is actually not possible. So a reference electrode, that is the hydrogen electrode, is taken. This consists of hydrogen gas at 1 atm pressure, which is in contact with a 1 molar solution of its ions at 298 K. So, and with respect to this hydrogen electrode, the standard electrode potentials are measured. So, here in table 1.13, the E0 values of elements here, they have been of various elements further, and their reduction potentials have been listed. So the electrode potential, it is a measure of the electropositive character. So as we can see that generally there is a decrease in electropositive character, and also the reactivity of the metals also decreases along a period. So in a period, the reactivity of the metals decreases, and there is also a decrease in the electropositive character. So here in table 1.3, the different values have been listed. Now if we plot of the variation of the electrode potential of a transition series of 3D elements, here it is shown in figure 1.16. So the unique behavior we particularly find for copper, because it has a positive E0. So that is the standard electrode potential. It accounts for its inability to liberate the hydrogen from dilute acids. Now when oxidizing acids, that is nitric and hot concentrated sulfuric acid, it reacts with copper, then the acids are being reduced. Else in general, copper cannot liberate hydrogen from dilute acids owing to its positive E0. So then coming to oxidation states, the transition elements, we know they usually exist in several oxidation states such as Fe3 plus, Fe2 plus and variable oxidation states. So the oxidation states that are exhibited by the transition elements, it may be related to particularly to their electronic structures and configuration. So, and we know particularly for transition elements, as they have the vacant d orbitals, so depending on the filling of the d orbitals, they have variable oxidation state and variable valency. So here in figure table 1.15, the oxidation state of some of the common d block elements and the most common oxidation states, it has been shown. So from looking at this table, here particularly in this table 1.15, we know that they follow a trend in a trend is followed. So the trend in stability of the oxidation states within the group, it is different for different transition elements, and they differ for the main group elements, that is the S and P block group elements, and for the main group elements, the oxidation state is also different. So here, so going to when we see the reactivity of some of the oxidation state of the first transition series in the elements that has been listed here in table 1.16, and their most stable oxidation state here has been listed for various types of elements. So the compounds that are present in their higher oxidation states, they are oxidizing in nature, and those the compounds where they are present in their lower oxidizing state, they are reducing and ionizing in nature. This is a one common trend that has been marked. Now the
Madam, voice is not audible.
କ୍ଲାସ୍ ହବ କି ଆଉ? ଭବାନୀ ସାର୍, ଭବାନୀ ସାର୍,
ଆପଣଙ୍କର କୋଉଠୁ ସାଉଣ୍ଡଟା ଆସୁଛି ଆପଣଙ୍କର?
हेलो हेलो किए अछंती केतरे? हाँ एथिरे क्लास केबेठु कोन स्टार्ट हेलानी केमिस्ट्री आ माने तर केमती कोन क्लास होउची एठी टिके कहबे कि जे भी अछंती अवेलेबल मु आज जॉइन करनी त मु किछ आज्ञा
आज तो फर्स्ट क्लास है।
कोड लिखा हैतला 20 तारिख रु बोली ए जरी
हाँ
18
आज तो
तारिख ना
20 तारीख सर।
सॉरी 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 तो एथि
आज
नोट
20
केमती कोन
तारीख ना।
सॉरी सॉरी नोट केमती कोन शेयरिंग एथिरे रहउची माने क्लास आरंभ होला परठारु
नोट सर किसी ना सेमती देखो आप सेल्फ स्टडी करेंगे एमती तो पाठ पढ़ा अच्छे
आ बही आपन किछ अवेलेबल हेलानी इग्नो तरफरु
हाँ सर मो पाख तो 4टा आसी
मो पाखरे
केबे
नाही मैं ऑफलाइन मारथिली बाकी बुक आज जाए आसेनी।
अच्छा मोर भी तो आसीनी एचे
ମୋର
एठी
ଚାରିଟା
भुवनेश्वर
ଆସିଛି।
स्टडी
ହ୍ୟାଲୋ ସାର୍ ମୋର ବି 4ଟା ଆସିଛି ଆଉ ଆଜି ବି କିଛି ବହି ଡେଲିଭରି ହେଇଛି ଘରକୁ ସେଟା ଜଣା ନାହିଁ କେତେଟା ଆସିଛି ଦେଖିଲେ ଜଣେଇବି ଗ୍ରୁପରେ ଆଉ।
ଆପଣଙ୍କୁ ଯଦି କିଛି ଆସିଥିଲା ତ ଭାୟା ପୋଷ୍ଟାଲ ର
ଅର୍ଡର
ଏନିକ
କରିଥିଲି
ମାନେ
କି?
ଆଉ କିଛି
ନାଇଁ
ହ୍ୟାଲୋ
ପୋଷ୍ଟାଲରେ ସବୁ ଆସୁଛି ସାର୍ ପୋଷ୍ଟାଲରେ ସବୁ ଆସୁଛି।
ତ ଆପଣଙ୍କୁ କିଛି ନମ୍ବର ଯୋଉ
ନାଇଁ
ଆପଣଙ୍କର
ଅର୍ଡର କରିବାକୁ ପଡୁଛି କି? ଆଜ୍ଞା କଣ ଅର୍ଡର କରିବାକୁ ପଡୁଛି କି ନା ଏମିତି ଆସୁଛି?
नहीं नहीं
ଏମିତି
मैडम
ଆସିବ ନା ଆମେ
पोस्टल
ତ ଅଫ୍ କରିଥିଲେ ସେଠି
ନାଇଁ ନାଇଁ ପୋଷ୍ଟାଲରେ ଆସିବ। ଆପଣ ଆପଣ ମାନେ ଆପଣ ଯେତେବେଳେ ଫର୍ମ ମାନେ ଯେତେବେଳେ ପକେଇଥିବେ ସେତେବେଳେ ତ ନମ୍ବର ଫମ୍ବର ଦେଇଥିବେ, ଆଡ୍ରେସ ଦେଇଥିବେ, ସବୁ ତ ସେଠି ଥିବ ନା। ତ ସେ ପୋଷ୍ଟାଲରେ ହିଁ ବୁକ୍ ଗୁଡା ପଠେଇଦେବେ। ଆଉ ମୋର ଥରେ ଆସିଥିଲା 4ଟା, ଆଜି ବି ଆସିଛି, ପହଞ୍ଚିଛି, କିନ୍ତୁ କେତେଟା ଅଛି ସେଟା ଯେହେତୁ ଘର ଆଡ୍ରେସ ଦେଇଥିଲି ତ ସିଆଡେ ମାନେ ଆସିଛି, ସେଟା ମୁଁ ଆଉ ଜାଣିନି କେତେଟା ଅଛି। ଦେଖିଲେ
ଆଚ୍ଛା
ମ୍ୟାଡାମ
ମୁଁ
ଟିକେ
ଜଣେଇଦେବି ଗ୍ରୁପରେ।
ଟିକେ ଶୁଣନ୍ତୁ, କ୍ଲାସ
ଯୋଉଟା
ଟାଇମିଂ
ମ୍ୟାଡାମ
କେତେଟା? ସେଇ
ଆସିବ
6ଟାରୁ 8ଟା ରହିବ ସବୁଦିନ?
ମେ ବି
ନାଇଁ
ମତେ
ନାଇଁ ସାର୍
ଲାଗୁଛି
ଦେଖ,
ସବୁଦିନ।
ନାଇଁ 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 ମ୍ୟାଡାମ, ଆପଣ ସେ ଆମର ଯୋଉ ଗ୍ରୁପ ରେ ସେୟାର ହେଇଥିଲା ଦେଖିଛନ୍ତି ନା ନାଇଁ ଦେଖିନାହାନ୍ତି? ଏଇ
ହଁ ହଁ
ସପ୍ତାହର 10, 11 ହଁ ସେତିକି ହିଁ କ୍ଲାସ ହବ।
ଗୋଟେ ମେସେଜ ପଠେଇଛନ୍ତି ନା,
ଆଚ୍ଛା।
ଟେକ୍ସଟ ମେସେଜ କରିଛନ୍ତି, ଟୋଟାଲ ସ୍କେଡ୍ୟୁଲ ପଠେଇଛନ୍ତି।
ହଁ ସ୍କେଡ୍ୟୁଲ ତ ପଠେଇଛନ୍ତି। ମୁଁ କହିବା କଥା କ୍ଲାସ ଟା ଯଦି ସ୍କେଡ୍ୟୁଲ ଟା ବର୍ତ୍ତମାନ ସମୟ ପାଇଁ ହିଁ କରିଥିବେ, ତାପରେ ଯଦି କିଛି ଅପଡେଟ ଆସିବ, ମଡିଫିକେସନ ହେଲେ, ତ ସେମିତି କିଛି ଅଛି କି?
ଦେଖନ୍ତୁ
ସେଇଟା
ସାର୍
ମେ ବି
ଆଜି ତ
ସେମାନେ ଜଣେଇଦେବେ ଗ୍ରୁପରେ ନା।
କୋଉ ଗ୍ରୁପ ରେ? ଗ୍ରୁପ ତ କିଛି ବି କ୍ରିଏଟ ହେଇନି।
ନାଇଁ ନାଇଁ,
ଗ୍ରୁପ
ଜାନୁଆରୀ ସେସନ ର ଯୋଉଥିରେ କି ଆମର ସାର୍ ଅଛନ୍ତି ନା, ସେ ଯୋଉ ଜଣେ ସାର୍ ଅଛନ୍ତି, କଣ ତାଙ୍କ ନା, ପ୍ରଭାକର ସାର୍। ସିଏ ତ ମାନେ A to Z ସବୁ ଜଣେଇ ଦିଅନ୍ତି ସେ ଗ୍ରୁପରେ ନା।
କୋଉ ଗ୍ରୁପ ରେ କହିଲେ? ମୁଁ ତ କୋଉ ଗ୍ରୁପ ରେ ଆଭେଲେବଲ ନାହିଁ।
ଆଡମିସନ କରିଥିଲୁ।
ଆଜ୍ଞା
ଜାନୁଆରୀ ସେସନ
ମୁଁ କହିଲି ଆମେ
ମତ-
ଜୁଲାଇ ସେସନରେ ଆଡମିସନ କରିଥିଲୁ, ସେଇଥିପାଇଁ ସାୟଦ ବୁକ୍ ଆସିନି।
ହଁ ହଁ
ଜୁଲାଇ ସେସନ
ନାଇଁ
ବାଲାଙ୍କର ଏତେ ଜଲଦି ଆସିବନି। ଆପଣ ଏଇ ଯୋଉ କ୍ଲାସ ଟା ଜଏନ କରିଛନ୍ତି, ଏଇଟା ଜାନୁଆରୀ ସେସନ ର କ୍ଲାସ ଟା।
ଓ ଆଚ୍ଛା, ଜୁଲାଇ
ଜାନୁଆରୀ
ସେସନ।
ଆମକୁ ମାନେ ଆସିଲା ମେସେଜ, ତ ସେଥିପାଇଁ ଆମେ ଜଏନ କରିଗଲୁ। ମୁଁ ବି ସେ ଭାବୁଥିଲି କି ଫାଷ୍ଟ ଗୋଟେ ସେ କହିଥିଲେ କି ସେଇଠି ଇଣ୍ଡକ୍ସନ କ୍ଲାସ ହବ ବୋଲି। ଆଜି ଯାକେ କିଛି ବି କ୍ଲାସ
ନାଇଁ ନାଇଁ, ଏଇଟା ଆପଣଙ୍କର, ଏଇଟା
ସେଟା
ଆପଣ
ଜୁଲାଇ
ମାନେ
ସେସନ ଟା।
ଯେହେତୁ ହୋଲ ଉପରେ,
ଓ
ହଁ
ଆଚ୍ଛା।
ହଁ, ଏଇଟା ଜାନୁଆରୀ ସେସନ ର
ତ
କ୍ଲାସ ଟା ବର୍ତ୍ତମାନ ଚାଲୁଛି, ବୁଝିଲେ କି? ଜାନୁଆରୀ ସେସନ ର
ହଁ
କ୍ଲାସ
ହଁ
ଆଜିଠୁ ଷ୍ଟାର୍ଟ ହେଲା। ଆଉ ଆମର ଜାନୁଆରୀ ସେସନ ର ହିଁ ବୁକ୍ ଗୁଡା।
ତାହେଲେ
ଓହୋ।
ଜୁଲାଇ ସେସନ ଆପଣ ଯଦି ଆଇଡିଆ ଅଛି, ପୁରୁଣା ଷ୍ଟୁଡେଣ୍ଟ, ତ ଜୁଲାଇ ସେସନ କେବେଠୁ ଷ୍ଟାର୍ଟ ହବ? ଆଉ ମାନେ ଜୁଲାଇ ସେସନ ର ବହି
ନାଇଁ
କେବେଠୁ
ସାର୍,
କିଛି?
ଶୁଣନ୍ତୁ ସାର୍, ଆପଣଙ୍କର ଜୁଲାଇ ସେସନ ର ଆଡମିସନ ସରିନାହିଁ।
ଆଚ୍ଛା ଆଚ୍ଛା, ନାଇଁ
ଅଗଷ୍ଟ 31
ସରି
ରୁ
ଯାଇଥିଲା ବୋଧେ, ତ କ୍ଲାସ ଟାଇମିଂ ଏକ୍ସଟେଣ୍ଡ ହେଇଥିଲା, ତାପରେ ସରି ଯାଇଥିଲା ବୋଧେ।
ନାଇଁ ନାଇଁ, ଆଉ ଥରେ ବଢିଲା ନା, ଅଗଷ୍ଟ 31 ଯାଏ ବଢିଲା, ଏକ୍ସଟେଣ୍ଡ ହେଲା।
ଓ ଆଚ୍ଛା ଆଚ୍ଛା।
ସାର୍ ଶୁଣନ୍ତୁ, ଆପଣଙ୍କର 31 ଅଗଷ୍ଟ ଯାଏଁ ସରିବ। ତାପରେ କେତେ ଜଣ ଛୁଆଙ୍କର ସମସ୍ତଙ୍କର କନଫର୍ମେସନ ହବ, ତାପରେ ଯାଇକି ସିଡ୍ୟୁଲ ତିଆରି ହବ।
ଆଚ୍ଛା, ଜାନୁଆରୀ
ତାପରେ
ସେସନ ରୁ କିଏ ବି
ବୁକ୍ ଆପଣ ଧରି ନିଅନ୍ତୁ, ମାସେ ଆପଣ ଧରି ନିଅନ୍ତୁ, ମାନେ ମାସେ କି ତାଠୁ ଏକ୍ସଟେଣ୍ଡ, ମାନେ ଅଧିକା ବରଂ ହବ ବୁକ୍ ଆସିବାରେ, କମ ହବନି, ବୁଝିଲେ
ଆଚ୍ଛା
କି? ଆମର ତ
ପାଖାପାଖି
ଜାନୁଆରୀ
ନଭେମ୍ବର
ସେସନ ରୁ
ଡିସେମ୍ବର।
ଆମେ ଆଡମିସନ କରିଥିଲୁ।
ଟିକେ ଶୁଣିବେ କି?
ହଁ, ଆମର ଆସିଲା ମାନେ
ଟିକେ ମୋ କଥା ଶୁଣିବେ କି? ଜାନୁଆରୀ
ଆଜ୍ଞା।
ସେସନ ପୁରୀ ପାଖାପାଖି ପିଲା କିଏ ଅଛନ୍ତି କି? ମାନେ ମୁଁ ତାଙ୍କ ଠାରୁ ବହି କଲେକ୍ଟ କରିଦିଅନ୍ତି ଆଗୁଆ ଟିକେ। ମୁଁ ଜବ୍ କରୁଛି ତ, ମତେ ଟିକେ ଅସୁବିଧା ହଉଛି ପଢାପଢି କରିବା ପାଇଁ। ପୁରୀ ପାଖାପାଖି କିଏ ଅଛନ୍ତି କି?
ସମସ୍ତେ ସାର୍ ଜବ୍ ବାଲା ଅଛନ୍ତି।
ମୁଁ
ଆମେ
ଜବ୍
ତ
ଅଫ୍
ସବୁ
କରିନଥିଲି, ମୁଁ ଛାଡିବି।
ପୁରୀ ତ ଆମର
ନାଇଁ, ସେ ଟେଲିଗ୍ରାମ ଗ୍ରୁପ ରେ ଅଛନ୍ତି ନା, ସେଠି କିଏ କିଏ ଜଣେ ସେୟାର କରିଦେବେ।
ପୁରୀ ପାଖାପାଖି ପିଲା କିଏ ଅଛନ୍ତି କହୁନାହାନ୍ତି, ନହେଲେ ମୁଁ ଯାଇକି ନିଜେ ନେଇ ଆସିବି।
ମୁଁ ତ ନୁହଁ, ଆମେ ବୋଧେ ଏଠି କେହି ନାହୁଁ, ନହେଲେ ତ କହିଥାନ୍ତେ।
ବି ଥିବ, ସେମାନେ ବୁକ୍ ର ବାକି ପିଡିଏଫ ଟା ସେ ଗ୍ରୁପ ରେ ସେୟାର କରିଦେଲେ, ଯାହାର ବି ଦରକାର ସେ ପ୍ରିଣ୍ଟ କାଢିଦେବେ।
ହଁ, ବୁକ୍ ପିଡିଏଫ ବି ଆପଣଙ୍କର ସେଇ ଯୋଉ ମାନେ ଗୋଟେ ଲିଙ୍କ ସିଏ ଛାଡିଦେବେ। ଆପଣ କିଛି ବି ବ୍ୟସ୍ତ ହବା ଦରକାର ନାହିଁ। ଆମର ଜାନୁଆରୀ ସେସନ ରେ ଯେତେବେଳେ ଡିସେମ୍ବରରେ ଆମର ମାନେ ଯୋଉ ସବୁ
ଆଉ
ଫର୍ମ ପକେଇ ସାରିଲୁ ଜାନୁଆରୀ ସେସନ ପାଇଁ, ତ ଆମର କନଫର୍ମେସନ ଆସିଲା ମାର୍ଚ୍ଚ ମାସରେ ଯାଇକି, ବୁଝିଲେ କି? ମାର୍ଚ୍ଚ ମାସରେ କନଫର୍ମେସନ
ଶୁଣୁନାହାନ୍ତି,
ଆସି ସାରିଲା।
ଶୁଣୁନାହାନ୍ତି, ଏ ଯୋଉ କୋଶ୍ଚିନ୍
ଆଜ୍ଞା।
କେମିତି ଏକ୍ସାମ ରେ ପଡୁଛି?
କୋଶ୍ଚିନ୍ ସେଗୁଡା ସବୁ ଆପଣଙ୍କୁ ଅନଲାଇନରେ, ସେ ଯୋଉ ଇଗ୍ନୋ ୱେବସାଇଟ ରେ, ମାନେ ଆପଣଙ୍କର ଜୁଲାଇ ସେସନ ର ଗୋଟେ ସେପାରେଟ ଗୋଟେ ଗ୍ରୁପ ହବ। ଠିକ ଅଛି, ଗ୍ରୁପ ଯିଏ କ୍ରିଏଟ କରିବା କଥା କରିଦେଇକି, ସେଇଥିରେ ହିଁ ସବୁ ଲିଙ୍କ ଆପଣଙ୍କର ପଳେଇ ଆସିବ। ନହେଲେ ମେଲ ଆଇଡି କୁ ଲିଙ୍କ ପଳେଇ ଆସିବ ସାର୍, ଆପଣ ବ୍ୟସ୍ତ ହୁଅନ୍ତୁନି।
ନା ନା, ମୁଁ କହିଲି କୋଶ୍ଚିନ୍ ଏକ୍ସାମ ରେ କେମିତି କଣ ଅଛି? ପାଠ ସହିତ ଟଚ୍ ନାହିଁ, ବହୁତ ଦିନ ହେଇଗଲା। ବିଇଡି ସରିଲା ପରେ ମୁଁ ଏଠି ଆଡମିସନ କରିଥିଲି ତ।
ଆମର ବି ସେଇ ସେମ ପ୍ରୋବ୍ଲେମ ସାର୍। ଆମେ ବି ମାନେ ଭାବୁଛୁ କି କେମିତି କଣ, ତ ନିଜେ ଏବେ ଟ୍ରାଏ କରୁଛୁ ସେମିତି ଧୀରେ ଧୀରେ, ବୁଝିଲେ କି?
ନାଇଁ,
ଆଉ
କୋଶ୍ଚିନ୍ କେମିତି କଣ ରହୁଛି? ମାନେ ଶୁଣୁନାହାନ୍ତି, କୋଶ୍ଚିନ୍ କେମିତି, ମାନେ ଡିସ୍କ୍ରିପଟିଭ୍ ପେପର ଟାଇପ ର ନା କେମିତି କଣ? ମୋର ପଢା ପୁରା ଟଚ୍ ଛାଡିଲାଣି। ଗ୍ରାଜୁଏସନ ମୋର 19 ରୁ ସରିଲାଣି, ତ ମୁଁ ଏପଟେ ଜବ୍ ହିଁ କରୁଛି ବ୍ୟାଙ୍କରେ।
ସାର୍ ଶୁଣନ୍ତୁ, ହ୍ୟାଲୋ,
କହୁନାହାନ୍ତି।
ଏବେ ସବୁ
हेलो
ଲଙ୍ଗ क्वेश्चन एठे शॉर्ट क्वेश्चन नहीं सर
अच्छा लॉन्ग क्वेश्चन माने केमती कोन आसुची तो इनऑर्गेनिक माने कॉन्सेप्चुअल बेस ना माने किछि एनालिटिकल आइडियोलॉजी जेंति +3 रे थिला
नहीं सर सुनो तो आपनकर पेपर अलगा ना एनालिटिकल एते कोन आसो
अच्छा
इनऑर्गेनिक अछि सब
ए
अछि
पूरी भुवनेश्वर पिला की अछंती पाखा कि निमापड़ा हम घर तो मु जाई नै आसंती हेलो
हेलो मैम सुनंतु
हां
हेलो
कोना दी
केमिस्ट्री रो प्रीवियस इलेक्टिव କିଛି ବି अपलोड ହେଇନି वेबसाइट रे सर्च
इलेक्टिव
कले तो जो मोर इलेक्टिव पेपर टा मु भूल चूज कर देछि सेटा माने रेक्टिफाई करी हबो कि जुलाई सेशन विषय
सेटा हम कहि
हाँ
फिर
नहीं मैडम
जो
आपण
मोर
इग्नोर सुनो स्टूडेंट
आगे
पोर्टल को जाके इग्नोर आपण ग्रीवेंस रे जिबे आपण कंप्लेंट
ग्रीवेंस
देकी
रे
सेठी
नहीं ग्रीवेंस रे प्रोग्राम टा MSc-CHM टा नहीं प्रोग्राम
आपण
चूज
नने
कले सेटा आसुनी
सुनो नने आपण ऑफिस भी जानदरी ऑफिस भी जाके थारे डायरेक्टर को सहित
ऑफिस
सांग
को भी
सहित कथा
जाइथिले से
हेबे
माने कहले कि आउ कंफर्मेशन हला परे हमें आउ किछि करि परिबुनी बोली ग्रीवेंस रे दियंतु बोली कहली किंतु ग्रीवेंस रे तो सेमती MSc केमिस्ट्री पय किछि नाही प्रोग्राम पे
नहीं हाँ मैडम सुनतु आसु नथिबे जे आपण शो करके किछि लेखिकी अलगा आईडी रे दियंतु से जो एनालिटिकल
मोर
केमिस्ट्री रे
जो
दियंतु
मोर
प्रदीप सर
PCM
आपन
बैकग्राउंड
नंबर टा
तो
ଟିକେ ଦେବେ
मैथ
କି
बैकग्राउंड टा हेलो सर टिके सुनि बायोलॉजी बायोलॉजी इलेक्टिव नबा कथा ना मैथमेटिक्स टा मोर बैकग्राउंड टा
बायोलॉजी इलेक्ट्रिक
केमिस्ट्री क्वेश्चन तो किछि भी वेबसाइट रे अपलोड हेनी केमिस्ट्री रो
बायोलॉजी तो किछि भी नहीं
हाँ
जो
अच्छी ना
मैथमेटिक्स फॉर
बायोलॉजी अच्छी और
केमिस्ट आ
मैथमेटिक्स
बायोलॉजी
अच्छी
फॉर केमिस्ट गोटे अछि
बायोकेमिस्ट्री सेटा
और
अलगा ना
नहीं नहीं सर
मैथमेटिक्स
शुणु आपनकर हाँ गोटे अच्छी आपण से मैथमेटिक्स चूज करे ना हूँ बायोलॉजी चूज
बायोलॉजी
करिए देखो 15 नंबर पेपर MCM-15 अच्छी
अच्छा अच्छा मु देखिनी
हाँ
अब
तो
मोर
मोर
मन नहीं
जो PCM बैकग्राउंड अछि तो मु मैथ नबा कथा ना बायोलॉजी नबा कथा ସେଇଟା ଆପଣଙ୍କ ଇଚ୍ଛା ଅନୁସାରେ ଆପଣ ଯୋଉଟା ନେଇପାରିବେ ନା ସେ ଯୋଉ ପ୍ରୋଗ୍ରାମ ଗାଇଡ୍ ରେ ଲେଖା ହେଇଛି ମାନେ ମ୍ୟାଥମେଟିକ୍ସ ବ୍ୟାକଗ୍ରାଉଣ୍ଡ ଗୁଡା ବାୟୋଲୋଜି ନେବେ ଆଉ ବାୟୋଲୋଜି ବ୍ୟାକଗ୍ରାଉଣ୍ଡ ଗୁଡା ମ୍ୟାଥମେଟିକ୍ସ ନେବେ ବୋଲି ଲେଖା ହେଇଛି ତ ମୁଁ ଦେଖିଛି
अच्छा अच्छा
ତ ମୁଁ ମାନେ ଯେହେତୁ ମୋର PCM ବ୍ୟାକଗ୍ରାଉଣ୍ଡ ଟା ମୁଁ ବାୟୋଲୋଜି ନବା କଥା ତାହେଲେ ତ ମୁଁ ଚୁଜ୍ କରିଦେଇଛି ମ୍ୟାଥମେଟିକ୍ସ ପାଇଁ ଆଉ हेलो सर ମୋ କଥା ଟିକେ ଶୁଣିବେ हेलो सर
हेलो
केमिस्ट्री प्रीवियस ईयर क्वेश्चन किछि अपलोड अछि वेबसाइट रे खाली
प्रीवियस
केमिस्ट्री
ईयर
रा
नथिला एथरक एटा फर्स्ट जनवरी सेशन आरंभ होइतला सेकंड टा हला चली जेबे
माने इग्नो रे केमिस्ट्री ए ईयर ऐड होला ना कोन
फिजिक्स केमिस्ट्री एई वर्ष
हाँ
ऐड
हाँ
हेछि
ओहो
एटा फास्ट बैच एडमिशन ହେଇଛି तारा
तो से
प्रीवियस क्वेश्चन पढ़ेছি
मैं
ସେଇଥି ପାଇଁ ତ
जानना
ମୁଁ ପଚାରୁଛି क्वेश्चन केमती कोन आସୁଛି ମୁଁ ବି नर्वस
ठीक है
ଶୁଣନ୍ତୁ
जुलाई
ଆପଣ
सेमेस्टर एग्जाम टा केबे हो के जानछन्ती कि जनवरी सेशन डिसेंबर रे
ଶୁଣନ୍ତୁ
हबो
ଆଜି
ନାଇଁ एग्नो तो छुट्टी दिन
जनवरी
मानक रे ही
डिसेंबर
करे
ଡିସେମ୍ବର
तो
ଲାଷ୍ଟ
नहीं जुलाई सेशन आसे जो माने एडमिशन करिछु सेमनकर सेमेस्टर एग्जाम टा जुलाई सेशन कहि परिबो जनवरी सेशन एडमिशन को तो डिसेंबर रे सेमानकर एग्जाम हबो
जनवरी डिसेंबर रे हबो
हाँ ସେଇଟା 6 ମାସ ଡିଫରେନ୍ସ ରେ ହୁଏ ଯୋଉ କିନ୍ତୁ ଜୁନ ରେ ମାନେ ବୁକ୍ ରେ କିଛି ଆସିନଥିଲା ତ ସେଇଥିପାଇଁ ଡିସେମ୍ବର ରେ ହବ ତ ଆପଣ ଯଦି ଚାହିଁବେ ଫାର୍ଷ୍ଟ ସେମିଷ୍ଟର ସେକେଣ୍ଡ ସେମିଷ୍ଟର ସେଇଟା ଡିସେମ୍ବର ରେ ଦେଇପାରିବେ କିନ୍ତୁ ସେଇଟା ପସିବଲ ନୁହେଁ ତ ଫାର୍ଷ୍ଟ ସେମିଷ୍ଟର ଦେଇ ସାରିଲା ପରେ ଆପଣ ପୁଣି ଜୁନ ରେ ସେକେଣ୍ଡ ସେମିଷ୍ଟର ଦେଇଦେବେ
ନା ନା ଆପଣଙ୍କ
କିନ୍ତୁ
କଥାଟା ମୁଁ
ସେଇଟା
କ୍ଲିୟରଲି ବୁଝିପାରୁନି ଆପଣ କହିବା କଥା ଯେ ଜାନୁଆରୀ ମାସରେ ସପୋଜ ଗୋଟେ ଇଣ୍ଡିଭିଜୁଆଲ ଆଡମିସନ ହେଲା
ହୁଁ
ତ
ହୁଁ
ସେଇ କେସ ରେ ତାର ଫାର୍ଷ୍ଟ ସେମିଷ୍ଟର ଟା କେବେ ହବ
ଜୁନ ରେ ହେବା କଥା
ଆଚ୍ଛା ଜୁନ ରେ ବହି କେବେ କଣ ଆସୁଛି ତାର ସେମିତି କିଛି ନା ନାହିଁ
ହଁ ବହି ତ ଏବେ ଜାନୁଆରୀରେ କରିଥିଲେ ଏବେ ମାସ ହେଲା ମୋ ପାଖକୁ ବହି ଆସିଛି ସେ କି
ମାନେ
କହିପାରିବେ
ମାସେ ହେଲା
ଆମର
ଯୋଉ ଆସିଛି
ପ୍ରାକ୍ଟିକାଲ
ଶୁଣନ୍ତୁ
କେବେ
ମାସେ
ହବ
ହେଲା ଯୋଉ
ହଁ ମାସେ ହେଲା
ନା ନା ମୁଁ କହିଲି
କିଛି ଅଡିବୁଲ ହଉନି ଆପଣଙ୍କ ଭଏସ।
ମାସେ ହେଲା ଯୋଉ ବହି ଆସିଛି ସେଟା ଫାର୍ଷ୍ଟ ସେମ ର ନା ସେକେଣ୍ଡ ସେମ ର?
ମାସେ ହେଲା ଯୋଉଟା ଅଛି ସେଇଟା ମୋ ପାଖକୁ ଫାର୍ଷ୍ଟ ସେମ ହିଁ ଆସିଛି। ଫାର୍ଷ୍ଟ ସେମ ରେ ଅଛି।
ଆଚ୍ଛା ଓ ଆଚ୍ଛା ଆଚ୍ଛା
ତ
ଫାର୍ଷ୍ଟ ସେମ ତ ଅଲରେଡି ସରିଯିବଣି ନା, ଜୁନ ଯାଇକି ଅଗଷ୍ଟ ହେଲାଣି ଆସିକି।
ଯେ ସେଇଟା ଆମେ ଜାଣିନଥିଲୁ, ସେଇ ସାର୍ କଲ୍ କରିଛୁ, ସାର୍ କହିଲେ କି ସେଇଟା ଆପଣ ଦେଇପାରିବେ ଡିସେମ୍ବରରେ ଦେଇପାରିବେ, ନହେଲେ
ନା
ମାନେ
ନା
ତମେ ଫାର୍ଷ୍ଟ ସେମ ଟା ଡିସେମ୍ବରରେ ଦବ।
ଆଚ୍ଛା ଇଗ୍ନୋ କହିବା କଥା ଯେ ଆଇଦର ଜୁନ ରେ ଦିଅ ନହେଲେ ଦିଟା କମ୍ବାଇନ ହେଇକି ଡିସେମ୍ବର ରେ ଦିଅ। ତାର ମାନେ ବହି ବି ତମକୁ ଜୁନ ପରେ ମାନେ ଏକ୍ଜାମ ସରିଲା ପରେ ପ୍ରୋଭାଇଡ କରିବ।
ନା ନା ଏକ୍ଜାମ ସରିଲା ପରେ ନୁହେଁ, ଯେହେତୁ ମାନେ ଟିକେ ଡିଲେ ହଉଛି ବୁକ୍ ଆସିବାରେ, ସେଇଥିପାଇଁ ଡିସେମ୍ବର ଫାର୍ଷ୍ଟ ସେମିଷ୍ଟର ଟା ରଖିଛନ୍ତି।
ମୁଁ ବୁଝିପାରୁନି,
ଏବେ
ଆପଣ ଏବେ କହିଲେ ଜୁନ ରେ ହଉଛି ବୋଲି, ପୁଣି ଏବେ କହିଲେ ଡିସେମ୍ବରରେ, କେମିତି କଣ?
ଆଚ୍ଛା ସମ୍ବିତ ସାର୍
ନା
ଶୁଣନ୍ତୁ।
ଆମର ଫାର୍ଷ୍ଟ ସେମିଷ୍ଟର ଡିସେମ୍ବରରେ ହିଁ ହବ।
ହଁ କୁହନ୍ତୁ।
ସମ୍ବିତ ସାର୍
ଫାର୍ଷ୍ଟ
ଶୁଣନ୍ତୁ,
ସେମିଷ୍ଟର ଟା ଆମର
ଆପଣ ଏବେ
ଡିସେମ୍ବରରେ
ଜୁଲାଇ
ହିଁ ହବ।
ସେସନରେ ଆଡମିସନ କରିଛନ୍ତି?
ନାଇଁ ଜାନୁଆରୀ।
ମୁଁ
ନା
ତ ଜୁଲାଇ ଏଇ
ସମ୍ବିତ
ସେସନରେ
ସାର୍
ଆଡମିସନ କରିଛି।
ହୁଁ
ଠିକ ଅଛି ଶୁଣନ୍ତୁ, ଆପଣଙ୍କ ଡାଉଟ ଟା ଶୁଣନ୍ତୁ। ଆପଣ ଜୁଲାଇ
ହଁ
ଶେଷରେ ଯେହେତୁ ଆଡମିସନ କରିଛନ୍ତି, ଆପଣ
ହଁ
ଏକ୍ଜାମ ଦେବେ ନେକ୍ସଟ ଇୟର ଜୁନ ମନ୍ଥ ରେ।
ନେକ୍ସଟ
ଇଗ୍ନୋରେ
ଇୟର ଯାଇକି
ସେମିଷ୍ଟର ନେକ୍ସଟ ଇୟର ଆପଣ ଶୁଣନ୍ତୁ, ଇଗ୍ନୋରେ କଣ କରିଛି, ଚାରିଟି ସେମିଷ୍ଟର ବେସ୍ଡ ମାନେ ସିଲାବସ ତିଆରି କରିଛି, କିନ୍ତୁ ଏକ୍ଜାମ ଟା ଆନୁଆଲି କରୁଛି। ଆନୁଆଲି ମାନେ ଦିଟା
ଆଚ୍ଛା ଆଚ୍ଛା
ସେମିଷ୍ଟର
ହୁଁ
ଆଟ ଏ
ହୁଁ
ଟାଇମ
ହୁଁ
ୱାନ୍ସ ଦେବେ। ଆପଣ ଏବେ ଜୁଲାଇରେ ଆଡମିସନ କରିଛନ୍ତି,
ଆଚ୍ଛା
ନେକ୍ସଟ ଇୟର ଜୁନରେ ଟିକେ ଦେବେ।
ଆଜ୍ଞା
ତ ଆପଣଙ୍କର ବୁକ୍ କଥା କହୁଛନ୍ତି,
ଓ ଆଚ୍ଛା
ଆମେ ଯୋଉମାନେ ସବୁ ଜାନୁଆରୀ ସେସନରେ ଆଡମିସନ କରିଛୁ, ଆମର ବୁକ୍ ଏବେ ଯାଏଁ ଆସିନି, ମାନେ ଦିଟା ଫେଜ ରେ କଣ 7-8ଟା ଖଣ୍ଡେ ବୁକ୍ ଆସିଛି। ସେ ବି ଦିଟା ଯାକ ସେମରେ ମିଶେଇକି କମ୍ବାଇନ ହେଇକି। ଆଉ କ୍ଲାସ ଆପଣ ଆଜି ଜଏନ
ଆଚ୍ଛା
କରିଛନ୍ତି, ଆମର ଏଇ ଯୋଉ କ୍ଲାସ ଟା ହଉଛି ଜାନୁଆରୀ ସେସନ ର ପ୍ରଥମ କ୍ଲାସ ଆଜି ଆପଣ ଯୋଉଥିରେ ଜଏନ କରିଛନ୍ତି।
ଆଚ୍ଛା
ବୁଝିଲେ,
ଆଚ୍ଛା
ଜାନୁଆରୀ ସେସନରେ ଆମେ ଯୋଉ ଆଡମିସନ କରିଛୁ, ପ୍ରଥମ କ୍ଲାସ ହଉଛି ଆଜି। ତ ଆପଣ ବର୍ତ୍ତମାନ
ଆଚ୍ଛା
ଜଏନ କରିଛନ୍ତି ଜୁଲାଇରେ, ଜୁଲାଇ ଆଡମିସନ ଆପଣଙ୍କ କନଫର୍ମ ହେଇଗଲାଣି?
ଏପର୍ଯ୍ୟନ୍ତ ଚାଲିଛି ବୋଧେ, ଆଉ ଥରେ ଡେଟ୍ ଏକ୍ସଟେଣ୍ଡ ହେଇଥିଲା ମୁଁ ଆଉ ଦେଖିନି।
ନା ଆପଣଙ୍କର ଆଡମିସନ କନଫର୍ମ ହେଇନି?
ହଁ ମୋର ତ କନଫର୍ମ ହେଇଯାଇଛି, ମେଲ ଆସିଲାଣି। ମୁଁ
କନଫର୍ମ ହେଇଛି, ସେଥିପାଇଁ ଆମକୁ ମାନେ ମେସେଜ ଆସିଥିଲା ନା କି କ୍ଲାସ ଷ୍ଟାର୍ଟ ହବ, ଜଏନ କରିବ ବୋଲି।
ଆପଣ ଯୋଉମାନେ ଜୁଲାଇ ସେସନରେ ଆଡମିସନ କରିଛନ୍ତି, ଆପଣଙ୍କୁ ଆଜି ଇ ଲିଙ୍କ ଆସିଥିଲା କ୍ଲାସ ପାଇଁ?
ହଁ ଆସିଲାଣି।
ମାନେ
ନାଇଁ ଲିଙ୍କ
ମେସେଜ
ଗୋଟେ ସେ
ଆସିଥିଲା
ଆସିଥିଲା
ଅଫଲାଇନ
ଯେ
ମେସେଜ।
ଯାହା ବି ସ୍କେଡ୍ୟୁଲ ହେଇଛି ସେଇଟା ଦେଖିବା ପାଇଁ।
ନା ଆଜି ଯୋଉ ଏଇ କ୍ଲାସ ଟା ହଉଛି, ଏଇଟା ଆମ ଜାନୁଆରୀ ସେସନରେ ଯୋଉମାନେ ଆଡମିସନ କରିଥିବେ ସେମାନଙ୍କ ପାଇଁ ହଉଛି। ବାକି ଆପଣ
ମୋ
ମାନଙ୍କ
ଉପରେ
ପାଇଁ ମୁଁ
ଲେଖା
କହିପାରିବିନି, ଆପଣଙ୍କୁ ଯଦି
ହେଇଥିଲା
ଆସିବ
ଜାନୁଆରୀ
ନାଇଁ
ଆସିବ।
ନାଇଁ ଶୁଣନ୍ତୁ ଶୁଣନ୍ତୁ
2024 ବୋଲି।
ଟିକେ 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 ନଏଜ କରନ୍ତୁ, ଶୁଣନ୍ତୁ ଟିକେ। ହ୍ୟାଲୋ,
କୁହନ୍ତୁ।
ମୁଁ କହିବା କଥା ହେଲା, ଆମର ଜାନୁଆରୀ ଯୋଉ ଜୁଲାଇ ସେସନରେ ଯୋଉ ଆଡମିସନ କରିଥିଲୁ, ତ ସେମାନଙ୍କ ପାଇଁ ଗୋଟେ ଲିଙ୍କ ପ୍ରୋଭାଇଡ କରାହେଲା, ଯୋଉଥିରେ କିଛି ପିଡିଏଫ ରେ କାଟାଗୋରାଇଜ ହେଇକି ଅଛି ଯେ ଏଇ ସଟନ ଲିଙ୍କ ରେ ମାନେ ଜାନୁଆରୀ ସେସନ ହଉ କି ଏମାନଙ୍କର ଥିଲା, ତ ଉପରେ ଜାନୁଆରୀ ସେସନ ଲେଖା ହେଇଥିଲା, ଆମେ ଜଏନ କରିଯାଇଥିଲୁ। ନା କି ଜୁଲାଇ ସେସନ ରେ, ତ ଏଇଠି
ସେଇ
କନଫ୍ୟୁଜନ
କଥା
ହଉଛି ଯେ ମାନେ
ମୁଁ ଆପଣଙ୍କୁ କଣ କହୁଛି, କନଫ୍ୟୁଜନ ଆପଣ
ହଁ
କ୍ଲିୟର କରନ୍ତୁ। ବର୍ତ୍ତମାନ ଜୁଲାଇ ସେସନରେ ଆଡମିସନ ବୋଧେ କମ୍ପ୍ଲିଟ ହେଇନି। ଯୋଉମାନେ
ନା ନା
ନେଇଛନ୍ତି,
ହେଇନି ଏପର୍ଯ୍ୟନ୍ତ।
କାହିଁକି 15 ତାରିଖ ଲାଷ୍ଟ ଥିଲା ବୋଧେ?
15 ତାରିଖ ମୁଁ
ଏବେ ଆଉ
କହିପାରିବିନି,
ଜୁଲାଇ
ମୁଁ ଆଉ
15
ଏବେ ଏକ୍ସଟେଣ୍ଡେଡ ଡେଟ୍ ଆଉ ଦେଖିନି।
ଏବେ କଣ ଅଗଷ୍ଟ
ନାଇଁ
ଏକ୍ସଟେଣ୍ଡ
ସାର୍,
କରିଦେଇଛନ୍ତି।
ଦିଲ୍ଲୀପ ସାର୍, ହ୍ୟାଲୋ।
ହଉ ହଉ ମୋ ଫୋନ ସୁଇଚ୍ ଅଫ୍ ହେଲା, ମୁଁ ଟିକେ ପରେ କଥା ହଉଛି।
ହଁ ଯେହେତୁ କ୍ଲାସ ମାନେ ଆପଣ ଆଡମିସନ କନଫର୍ମ ହେଇନି, କ୍ଲାସ ବି ଆପଣଙ୍କର ହବ, ବ୍ୟସ୍ତ ହୁଅନ୍ତୁନି।
ଟିକେ କିଏ କହିପାରିବେ ଆମର ପ୍ରାକ୍ଟିକାଲ କେବେ ହବ ଜାନୁଆରୀ ସେକ୍ସନ ର?
ଆଚ୍ଛା ଶୁଣନ୍ତୁ ମ୍ୟାଡାମ, ଜାନୁଆରୀ ସେସନରେ ପ୍ରାକ୍ଟିକାଲ
ଆଜ୍ଞା
ଆମେ ଯାହା ଓରିଏଣ୍ଟେସନ କ୍ଲାସ ରେ ସାର୍ ଜଣେଇଥିଲେ, ଆମର ଯୋଉ ମଲ୍ଲିକ ସାର୍ ସମଥିଙ୍ଗ ସାର୍ ସେ
ଆଜ୍ଞା
କହିଥିଲେ କି ବର୍ତ୍ତମାନ ତାଙ୍କ ପ୍ରାକ୍ଟିକାଲ ଟା ଦିଟା ସେସନ ଟାଇମ ରେ କରନ୍ତି। ଗୋଟେ ୱିଣ୍ଟର ଭ୍ୟାକେସନ ଯୋଉଟା କି
ହୁଁ
ଆମ ଦଶହରା ଟାଇମ, ଆଉ ଗୋଟେ ରହୁଛି ସେପଟ ସମର
ଆଚ୍ଛା
ଭ୍ୟାକେସନ। ତ ବର୍ତ୍ତମାନ
ହୁଁ ହୁଁ
ୱିଣ୍ଟର ଭ୍ୟାକେସନ ପାଇଁ ସେମାନଙ୍କ ପ୍ରୋଗ୍ରାମ ନାହିଁ, ଯେହେତୁ ନୂଆ କୋର୍ସ ହେଇଛି। ସେମାନଙ୍କ
ହୁଁ ହୁଁ
ଯୋଉ ଦଶହରା ଟାଇମ ରେ ସେମାନେ କିଛି ଫିକ୍ସ କରିନାହାନ୍ତି, ଇକୁଇପମେଣ୍ଟ କି କିଛି ସେମିତି ଫିକ୍ସ ହେଇନି। ତେଣୁ ମୋଷ୍ଟ ପ୍ରୋବାବିଲି ଯେତେ
ଆଚ୍ଛା
ଦୂର ସମ୍ଭବ ନେକ୍ସଟ ଇୟର ସମର ଭ୍ୟାକେସନ ରେ ଦିଟା ଯାକ ସେମିଷ୍ଟର ଏକା ସାଙ୍ଗରେ କରିପାରନ୍ତି। ଆଉ ଯଦି ଫ୍ରିକୱେଣ୍ଟଲି
ତାମାନେ
ସେମାନେ
ଆମର
ଏଇ ଭିତରେ
ସେମିଷ୍ଟର
କରିଦେବେ,
ଥିଓରି ଆଗ ସାରିଦେବେ, ତାପରେ ପ୍ରାକ୍ଟିକାଲ କରିବେ ଆଉ।
ବାସ୍ ବାସ୍ ସେ ଯାହା କହିଲେ, ଆଉ କହିଲେ ମାନେ ଯଦି ହେଇଯାଉଛି ଆମେ ସେଟଅପ୍ କରିଦଉଛୁ, ତାହେଲେ ଆମେ ଏଇ ଦଶହରା ଟାଇମ ରେ ଟ୍ରାଏ କରିବୁ କରିବା ପାଇଁ। କିନ୍ତୁ ମୋଷ୍ଟ ପ୍ରୋବାବିଲି ଯେତେ ଦୂର ସମ୍ଭବ ଆମକୁ ଲାଗୁଛି ନେକ୍ସଟ ଇୟର ସମର ଭ୍ୟାକେସନ ହିଁ ଦିଟା ଯାକ ସେମିଷ୍ଟର ରେ କରିବୁ।
ଆଉ ଗୋଟେ କଥା ବୁଝିବାର
ହେଲେ
ଅଛି,
ସେ
ଆମର ଯୋଉ ଜାନୁଆରୀ ସେକ୍ସନରେ ଆଡମିସନ ହେଇଛି, ଆସାଇନମେଣ୍ଟ ଡିପୋଜିଟ ଲାଷ୍ଟ ଡେଟ୍ କେବେ କହୁଛନ୍ତି?
ସେପ୍ଟେମ୍ବର
ଦେଇଛନ୍ତି ବା ଗ୍ରୁପ ରେ
30
ଆପଣ ଦେଖିଥିବେ,
ସେପ୍ଟେମ୍ବର 30
ସେପ୍ଟେମ୍ବର
ସେପ୍ଟେମ୍ବର
23 ରୁ 30 ଭିତରେ।
ସେପ୍ଟେମ୍ବର ଲାଷ୍ଟ ଡେଟ୍।
ଆଚ୍ଛା ଆଚ୍ଛା, ହଉ
ସେପ୍ଟେମ୍ବର
ଧନ୍ୟବାଦ।
23 ରୁ 30 ଭିତରେ।
ଆଜ୍ଞା
ସାର୍
ଆଜ୍ଞା।
ଟିକେ ସାର୍, ହ୍ୟାଲୋ
ହଁ
ସାର୍।
କୁହନ୍ତୁ।
ସାର୍ ମତେ ଟିକେ ଜାନୁଆରୀ ସେସନ୍ ହ୍ୱାଟ୍ସଆପ୍ ଗ୍ରୁପରେ ଜଏନ୍ କରିପାରିବେ?
ଜାନୁଆରୀ ସେସନର ଅଫିସିଆଲ ହ୍ୱାଟ୍ସଆପ୍ ଗ୍ରୁପରେ ଆପଣ ନାହାନ୍ତି କି?
ନା ନା ମୁଁ ଜୁଲାଇ ସେସନରେ ଅଛି କିନ୍ତୁ ଜାନୁଆରୀ ସେସନରେ ଲିଙ୍କ ପାଇଲିନି ତ ଜଏନ୍
ଜାନୁଆରୀ କାହିଁକି
ହେଇପାରିଲିନି।
ଆପଣ ଆଡ୍ ହେବେ? ଆପଣ ଯେହେତୁ ଜୁଲାଇ ସେସନ ଆଡମିସନ କରିଛନ୍ତି, ଜାନୁଆରୀ ସେସନରେ ଯଦି ଆପଣ ଆଡ୍ ହେବେ ଆପଣ କନଫ୍ୟୁଜ ହେବେ କେତେବେଳେ ଆସାଇନମେଣ୍ଟ ପାଇଁ ଡେଟ୍ ଆସିବ ଆପଣ ଭାବିବେ ଆମ ପାଇଁ ଆସିଲା, କେତେବେଳେ ପ୍ରାକ୍ଟିକାଲ ପାଇଁ
ନା
ଡେଟ୍
ନା
ଆସିବ ଆପଣ ଭାବିବେ ଆମ ପାଇଁ ଆସିଲା, ତେଣୁ ଆପଣ କନଫ୍ୟୁଜ ହେଇଯିବେ।
ନା
ତା ସାଙ୍ଗରେ ଆଉ
ନା ସାର୍
ଯିଏ ବି ତିଆରି କରୁଛନ୍ତି,
ସାର୍ ଆମର ହ୍ୟାଲୋ ସାର୍
ସାର୍ ମୁଁ ଜାନୁଆରୀ ସେସନ ଆଡମିସନ କରିଛି ଜୁଲାଇ ସେସନରେ ନୁହେଁ।
ହଁ ଯୋଉମାନେ ଜାନୁଆରୀ ସେସନରେ ଆଡମିସନ ଚାହୁଁଛନ୍ତି ଅଲରେଡି ତ କୋଅର୍ଡିନେଟର ସାର୍ ଗ୍ରୁପ ଗୋଟେ କରିଛନ୍ତି, ଏବେ ବି ସମଥିଙ୍ଗ ଗୋଟେ କରିକି ସେଥିରେ ଆଡ୍ କରେଇଛନ୍ତି ସମସ୍ତଙ୍କୁ।
ଆକ୍ଚୁଆଲି ମୋର ରିଜନାଲ ସେଣ୍ଟର ଅନୁଗୁଳ କିନ୍ତୁ ମୁଁ ଭୁବନେଶ୍ୱରକୁ ଚେଞ୍ଜ କରିବି। ତ ସେଇଥିପାଇଁ ମୁଁ ଚେଞ୍ଜ ହେଇନି, ଏବେ ଗୋଟେ ଦି ଦିନ ଭିତରେ ଚେଞ୍ଜ ହେଇଯିବ ତାଙ୍କୁ ମେଲ୍ କରିଛି।
ହଁ ଆପଣ ଚେଞ୍ଜ ହେଇଗଲା ପରେ ସେଇ ଯିଏ ପ୍ରଭାକର ସାର୍ ମଲ୍ଲିକ ସାର୍ ସମଥିଙ୍ଗ ଅଛନ୍ତି ଆପଣ ସେଇଠି କହିଲେ ସେମାନେ ଆଡ୍ କରିଦେବେ, କାହିଁକି ନା କନଫର୍ମ ଯେହେତୁ ହେଇନି ସେମାନେ କରିନଥିବେ।
ହ୍ୟାଲୋ
ଆପଣ
ଚେଞ୍ଜ ଥିବ
ତାଙ୍କ ନମ୍ବର ଟିକେ ପ୍ରୋଭାଇଡ
ସାର୍
କରିପାରିବେ କି?
କଣ କହିଲେ?
ମୁଁ କହିଲି ପ୍ରଭାକର
ହ୍ୟାଲୋ
ସାରଙ୍କ ନମ୍ବର ଟିକେ ପ୍ରୋଭାଇଡ କରିପାରିବେ କି ଆପଣ ମତେ ଟିକେ କହିପାରିବେ କି?
ଆପଣଙ୍କୁ ଗ୍ରୁପରେ ଥିବ ଦେଖିଲେ ମେ ବି ଜଣା ପଡିବ। ବାକି ତାଙ୍କୁ ତ ଆମେ ମେସେଜ ବି କଲେ ସେ ବେଳେ ବେଳେ ଦେଖନ୍ତିନି, ବ୍ୟସ୍ତ ରହନ୍ତି କି କଣ କରନ୍ତି।
ଏବେ ଟିକେ ନମ୍ବରଟା ଦରକାର ଥିଲା।
ହ୍ୟାଲୋ ସାର୍ ହ୍ୟାଲୋ
ହ୍ୟାଲୋ
ଆଜ୍ଞା ସାର୍ ଏ ଯୋଉ
ସାର୍ ଟିକେ
ଆମର
ନମ୍ବରଟା ଟିକେ ସେଣ୍ଡ କରନ୍ତୁ।
ଜାନୁଆରୀ
ଜଏଣ୍ଟ
ସେକ୍ସନର
କୁହନ୍ତୁ ଆଜ୍ଞା
ହ୍ୟାଲୋ ସାର୍ ଆମର ଜାନୁଆରୀ ସେକ୍ସନର ତ
ଆଜ୍ଞା
ଆସାଇନମେଣ୍ଟ 4ଟା ପେପର ଆସିଥିଲା, ଆଉ
ହଁ।
ନେକ୍ସଟ ଆଉ ତ ଆସିନି ଏପର୍ଯ୍ୟନ୍ତ।
ନା ସେଟା କହିଲେ ଯେତିକି ଆସିଛି ଆପଣ ସେତିକି ଅପଡେଟ୍ କରିକି ଦିଅନ୍ତୁ, ବାକି ନେକ୍ସଟ ଆପଣ ବାଇ ଦ ଟାଇମ୍ ଆସିଯିବ। ଯେହେତୁ ଏବେ ପର୍ଯ୍ୟନ୍ତ ଆମର ସେକେଣ୍ଡ ସେମ୍ ପାଇଁ କିଛି ଆସିନି, ତାମାନେ ଆମେ ହୋପ ରଖିବା ଯେ ଆମର ଏଇ ଡିସେମ୍ବରରେ ଖାଲି ସେମିଷ୍ଟର 1 ପାଇଁ ହିଁ ବୋଧେ ଏକ୍ଜାମ ସେମାନେ କରିବା ପାଇଁ ପ୍ଲାନ୍ କରୁଛନ୍ତି କି କଣ?
ଆଜ୍ଞା ଆମେ
ଯେହେତୁ
ତାମାନେ
ଆସିନି ଆମେ ତ କାହିଁକି ହୋପ ରଖିବା।
ତାମାନେ ଆମେ ଏଇ 4ଟା ପେପର କେବଳ ଡିପୋଜିଟ୍ କରିବା।
ହଁ ଯେହେତୁ ସେକେଣ୍ଡ ପେପର ଆସିନି ତେଣୁ ଆମେ ସେକେଣ୍ଡ ସେମ୍ ଆସିନି ଫାଷ୍ଟ ସେମ୍ ଟା ହିଁ ଡିପୋଜିଟ୍ କରିବା। ଏଇ ଟାଇମ
ତାମାନେ ଏ
ଭିତରେ
ଯୋଉ
ଯଦି ଆସିଗଲା ତା ଟାଇମ ପୂର୍ବରୁ ତାହେଲେ ଆମେ ଦେଖିକି ତାଙ୍କୁ ରିକ୍ୱେଷ୍ଟ କରିବା କି ଏତିକି ଟାଇମ ଭିତରେ ଲେଖି ହଉନି, ତେଣୁ ସେମାନେ ଏକ୍ସଟେନସନ କରିପାରିବେ ନିଶ୍ଚିତ ରୂପେ।
ଆମେ ସାର୍ ସେପ୍ଟେମ୍ବର 30 ତ ଲାଷ୍ଟ ଅଛି ଆଉ ନାଇଁ?
ଆଜ୍ଞା ଆଜ୍ଞା ସେପ୍ଟେମ୍ବର 30 ସେ ତ ଥରେ ଫାଷ୍ଟ ଯେତେବେଳେ ଓରିଏଣ୍ଟେସନ କରିଥିଲେ ମାସେ ପୂର୍ବରୁ ସେତେବେଳେ କହୁଥିଲେ କି ସେପ୍ଟେମ୍ବର 30 ଟା ମେ ବି ଏକ୍ସଟେନସନ ହେଇକି ଅକ୍ଟୋବର 30 ଯାଏଁ
ଆଜ୍ଞା
ହେଇପାରେ।
ଆଜ୍ଞା
ଇଫ୍ ପସିବୁଲ ମାନେ ଯଦି ସେମିତି କିଛି ହାର୍ଡ କେସ୍ ଅଛି ତାହେଲେ ସେପ୍ଟେମ୍ବର 30 ଟା ଅକ୍ଟୋବର 30 ହେଇପାରେ, କିନ୍ତୁ ଯେପର୍ଯ୍ୟନ୍ତ ଫର୍ଦର ନୋଟିସ୍ ନ ଆସିଛି ଆପଣ ସେପ୍ଟେମ୍ବର 30 ଟା ଲାଷ୍ଟ
ଆଜ୍ଞା
ଡେଟ୍ ଭାବିକି
ହଉ
ଲେଖିକି
ସାର୍
ଦିଅନ୍ତୁ।
ଥ୍ୟାଙ୍କ ୟୁ ଆଜ୍ଞା।
ହ୍ୟାଲୋ ସାର୍ ସାର୍
ଆଜ୍ଞା।
ସାର୍ ମତେ ଏ ନମ୍ବରଟା ଟିକେ ପ୍ରଭାକର ସାରଙ୍କର।
ଶୁଣନ୍ତୁ ଆପଣ ଯୋଉଠି ଅଛନ୍ତି ଯୋଉ ଅନୁଗୁଳ ରିଜନାଲ ସେଣ୍ଟର ଅଛନ୍ତି ଆପଣ ସେଠୁ ଆସିନାହାନ୍ତି ଏଠିକି ନା, ସେଠୁ ଆସିଲେ ସେମାନେ ସବୁ କିଛି ଇନଫରମେସନ ଦେଇଦେବେ।
ଓକେ ସାର୍।
ହ୍ୟାଲୋ
ଆପଣ ଏଠିକୁ ଏପଟକୁ ଡାକିଲେ ସେମାନେ
ହ୍ୟାଲୋ
ଇନଫରମେସନ ଦେଇଦେବେ ସେଇ ରିଜନାଲ।
ହ୍ୟାଲୋ
ହଁ କହୁନାହାନ୍ତି।
ହ୍ୟାଲୋ ସାର୍ ସାର୍ ଆସାଇନମେଣ୍ଟ ଟା କଣ ସେପଟୁ ପଠେଇବେ ନା ନିଜେ କୋଉଠୁ ପେପର ଚୁଜ କରି କରାଯାଏ?
ଆସାଇନମେଣ୍ଟ ମାନେ କୋଶ୍ଚିନ୍ ତ ଆସିଛି ଆପଣ ନିଜେ ଲେଖିକି ଦେବେ।
ଆଚ୍ଛା ଆମେ ନିଜେ ପେପର ପ୍ରିଣ୍ଟ ଆଉଟ୍ କାଢି ଆମେ ନିଜେ ଲେଖିକି ଦବୁ।
ହଁ ପେପର ପ୍ରିଣ୍ଟ ଆଉଟ୍ କଣ କାଢିବେ, ଆପଣ ନିଜେ ପେପର A4 ସାଇଜ ପେପର ନେଇକି ଆସିବେ ମାର୍କେଟରୁ, ସେଥିରେ ଆପଣ ଆଉ କୋଶ୍ଚିନ୍ ତ ଅଛି ଆନ୍ସର ଲେଖିକି ଦେବେ ଆଉ।
ସେମିତି ଆଉ କିଛି ସେ ଇଗ୍ନୋ ତରଫରୁ କିଛି ଆସିବନି ଆଉ।
ନାଇଁ ନାଇଁ ଇଗ୍ନୋ ତରଫରୁ ସେମାନେ କୋଶ୍ଚିନ୍ ଦେଇଦେଲେ ଆମକୁ ଆନ୍ସର କରିକି ଦବାର ଅଛି, ଆନ୍ସର ଟା ନିଜେ ପେପରରେ ମେନସନ କରିଛନ୍ତି A4 ସାଇଜ ପେପର ବୋଲି। ତ A4 ସାଇଜ ରେ ଆମେ କରିକି ଦବା ଯେତେ ପସିବୁଲ ସେମାନେ ମୁଁ କହୁଥିଲି କି ସାର୍ ରୋଲିଂ ପେପରରେ ଦେଲେ ହବ କି, ସେ କହିଲେ ରୋଲିଂ ବି ଦେଇପାରିବେ ପ୍ଲେନ୍ ବି ଦେଇପାରିବେ ବଟ୍ A4 ସାଇଜ ହବା ଦରକାର। ମାର୍ଜିନ ବି ଆପଣ ଲେଫ୍ଟ ଆଉ ଟପ୍ ଟା ଛାଡିବା ନିହାତି ଜରୁରୀ। ଆଉ ସେଇଥିରେ ଆପଣ ରୋଲିଂ ଟା ବି ଚୁଜ୍ କରନ୍ତୁ, କିନ୍ତୁ ଆମ କେମିଷ୍ଟ୍ରି ଯେହେତୁ ଆମେ ଅଛେ ଆମ କେମିଷ୍ଟ୍ରିରେ କିଛି ରିଆକ୍ସନ ବଗେରା ଡାଇଗ୍ରାମ ବଗେରା ଥିବ ତ ଆମେ ରୋଲିଂ ପେପର କଲେ ସେଟା ପ୍ରୋବ୍ଲେମ ହେଇପାରେ, ଗ୍ରାଫ ଫ୍ରାଫ ସବୁ ଅଛି ସେଗୁଡାକ କରିବାରେ ଟିକେ ପ୍ରୋବ୍ଲେମ ହେଇପାରେ, ତେଣୁ ରୋଲିଂ ପେପର ପ୍ଲେନ୍ ପେପର କଲେ ମାନେ କନଭିନିଏଣ୍ଟ ହବ।
ରୋଲିଂ ଆଉ ହ୍ୟାଲୋ ସାର୍ ହ୍ୟାଲୋ ସାର୍ ହ୍ୟାଲୋ
ଆଜ୍ଞା
ଆଜ୍ଞା ସାର୍ ମୁଁ କହୁଥିଲି କଣ କି ଆମର ଯୋଉ ଇଲେକ୍ଟିଭ କୋର୍ସ ଟା ଯୋଉ ମ୍ୟାଥ ଆଉ ବାୟୋଲୋଜି ଅଛି
ଆଜ୍ଞା
ତାକୁ ଆମେ ତ ଯେକୌଣସି ଗୋଟେ ନେଲେ ଚଳିବ ନା PCM ପାଇଁ CBZ ପାଇଁ ସେମିତି କିଛି ଅଛି କି?
ଶୁଣନ୍ତୁ ମ୍ୟାଡାମ ଆପଣ ଯୋଉ ପ୍ରଶ୍ନ
ଆଜ୍ଞା
ପଚାରୁଛନ୍ତି ନା ମୁଁ ବି ସେଇଥିରେ ଡାଉଟରେ
ଆଜ୍ଞା
ଅଛି, କାହିଁକି ନା ସେ ଯୋଉ ପ୍ରୋସ୍ପେକ୍ଟସ ଦେଇଛନ୍ତି ସେଥିରେ ଲେଖିଛନ୍ତି ମ୍ୟାଥମେଟିକ୍ସ ବ୍ୟାକଗ୍ରାଉଣ୍ଡ ପାଇଁ ବାୟୋଲୋଜି
ଆଜ୍ଞା
ଚୁଜ୍ କରିବେ बायोलॉजी बैकग्राउंड में
ଆଜ୍ଞା
मैथमेटिक्स चूज
ଆଜ୍ଞା
करिए मु तो निजे पीसीएम बैकग्राउंड रोटे किंतु मैथमेटिक्स देइथिली जेतु जानि नथिली पूर्वरु
ଆଜ୍ଞା
तो मु जाइथिले थर ऑफिस को भी तमर रीजनल ऑफिस को एई रिगार्डिंग कहया पई से कहले आमे
ଆଜ୍ଞା
किछि करि परिबनी आपण ग्राइडेंस दियंतु मेल करंतु
ଆଜ୍ଞା
तापरे जदि किछि रेस्पॉन्स आछे ताहले पुडु से माने करिवे हम पाखरे किछि नाही
ତାହେଲେ ମୋର ବି ସେମ୍ କେସ୍ ପିସିଏମ୍ ମୁଁ ମ୍ୟାଥରେ କରିଛି ହେଲା କି ଆଉ
पीसीएम मैथ मु
ତେଣୁକରି
भी सेम
ଆମେ
करथिली ये सेमति
ଏବେ
तो
ବି
मते लागुनी जे
ଆସାଇନମେଣ୍ଟରେ
मेजर इशू
ମ୍ୟାଥ
हबो बोली
ମତେ ଲାଗୁଛି ଚଳିବ ବୋଧେ
मेजर
କାହିଁକି ନା ଆଜ୍ଞା
ମ୍ୟାଡାମ ଶୁଣନ୍ତୁ ସେ ସେମ୍ କେସ୍ ପାଇଁ ମୁଁ ବି ଯାଇଥିଲି ସେମାନେ
ଆଜ୍ଞା
କହିଲେ ଯଦି ତମର ରେଜିଷ୍ଟ୍ରେସନ ବେଳେ ୱାନ୍ସ ନେଇଯାଇଛି ତାହେଲେ କିଛି ଅସୁବିଧା ନାହିଁ ଆପଣ ସେଇ ପେପର ଚୁଜ୍ କରି ଲେଖିବେ
ଆଜ୍ଞା
ଆମର ଜେନେରାଲ ବୁଝିଲେ
ଆଜ୍ଞା
ତେଣୁ ସେଥିପାଇଁ ଓରିଡି ହୁଅନ୍ତୁନି
ଆଜ୍ଞା ଆଜ୍ଞା
ସେ ତ କହିଲେ କି କିଛି ମାନେ ଆପଣ ଯଦି ବା ଚାହୁଁଛନ୍ତି ଚେଞ୍ଜ କରିବା ପାଇଁ ଆପଣ ଗ୍ରାଇଡେନ୍ସ କରନ୍ତୁ ଆମ ପାଖରେ ଆମେ କିଛି କରିପାରିବୁ କିଛି ବି ତାର ଆକ୍ଟିଭ
ନାଇଁ ସେ ଚେଞ୍ଜ କରିବାନି ସେ
ଯଦି କରିବେ
ଯେହେତୁ ଗୋଟେ
ନା ସେଟା
ବ୍ୟାକଗ୍ରାଉଣ୍ଡ
ଗୋଟେ
ଅଛି
ଆମର ଯୋଉ ଷ୍ଟୁଡେଣ୍ଟ ଆଇଡି ଯୋଉ ଅଛି ଷ୍ଟୁଡେଣ୍ଟ ଆଇଡିରେ ଚେଞ୍ଜ ହେଇପାରୁଛି କିନ୍ତୁ ଚେଞ୍ଜ ହବାଟା ଟିକେ ଇଏ ଡିଫିକଲ୍ଟ ହଉଛି ସେ କଣ
ତାପରେ
ତାର ଗୋଟେ
ମ୍ୟାଡାମ
ରିଡିଂ
ଶୁଣନ୍ତୁ ଆମର ମ୍ୟାଥ ଆମର ପିସିଏମ୍ ବାଲା ମ୍ୟାଥ ଆମର ସୁଇଟେବଲ
ମୁଁ ବି ନିଜେ
ବାୟୋଲୋଜି ତ ଆମେ କିଛି
ପିସିଏମ୍ ମୁଁ ବି
ଜାଣିନାହାନ୍ତି
ନିଜେ ମ୍ୟାଥ ନେଇଛି ତାପରେ ମୁଁ ଯେତେବେଳେ ମୁଁ ଆକ୍ଚୁଆଲି ପ୍ରୋସ୍ପେକ୍ଟସ ଟା ଦେଖିନଥିଲି ମୋର ଲାଷ୍ଟ ଡେଟ୍ ଥିଲା 30 ଥିଲା ମୁଁ 29 ଏମିତି କରିଦେଇଥିଲି ତାପରେ ଦେଖିଲି ଯେତେବେଳେ ପ୍ରଭାକର ସାର୍ ଙ୍କୁ ପଚାରିଲି କହିଲେ ସେଥିପାଇଁ କିଛି ଦେଖ ତମର ଯଦି ହେଉଛି ହେଇଯାଉ ନା ନେଇଯାଇଛି ଯଦି କିଛି ଅସୁବିଧା ହବନି ତମର ଯୋଉଟା ଅଛି ସେଇଟା ଲେଖିବ
ଆଜ୍ଞା ଆଜ୍ଞା
ଆଉ ତାପରେ ସେଟା ଚେଞ୍ଜ କରିବା ପାଇଁ ଦେଖାଇଲା ବେଳକୁ ସେଟା ଟିକେ ଡିଫିକଲ୍ଟ ହଉଛି
ହଁ
ତେଣୁ
ଚଳିବ
ଆପଣ
ତାହେଲେ
ଦେଖନ୍ତୁ
ଠିକ
ଯଦି
ଅଛି
ହେଇପାରିବ ହେଇପାରିବ
ଆଜ୍ଞା ଆଜ୍ଞା
ବାକି କ୍ଲାସ ତ ରଖିଥିଲି 8ଟା ଯାଏଁ 7ଟା ବେଳକୁ କଣ କନେକ୍ସନ ପ୍ରୋବ୍ଲେମ ହେଲେ କି ସେ କଣ ହେଲା 7ଟା ଭିତରେ ରହିଗଲେ କଣ ହେଇଥିବ ସେମାନଙ୍କର ସେପଟ ସାଇଡ ରୁ
କନେକ୍ସନ ସାର୍ ପ୍ରୋବ୍ଲେମ ଥିବ ସେଥିଲାଗି
ହଁ
କାଟିଛନ୍ତି।
କାହିଁକି ନା ସେ ତ ଯଦି ୱାଇଣ୍ଡ ଅପ୍ କରିଥାନ୍ତେ ସାର୍ ସେ କହିକି ୱାଇଣ୍ଡ ଅପ୍ କରିଥାନ୍ତେ କି ଆଜି ପାଇଁ ଏତିକି ନେକ୍ସଟ କ୍ଲାସରେ ଆମେ କିଛି ପଢିବା ମେ ବି କନେକ୍ସନ ଆପଣ ଯାହା କହୁଛନ୍ତି କନେକ୍ସନ ପ୍ରୋବ୍ଲେମ ହିଁ କିଛି ବୋଧେ ଥିବ ନାଇଁ ହଠାତ୍ ରେଗୁଲାର କ୍ଲାସରେ କଟିଗଲେ
ଦେଖନ୍ତୁ ସାର୍ ଆଉ ଟିକେ ପରେ କିଛି ଆସିପାରନ୍ତି ବୋଧେ ସେ ମ୍ୟାଡାମ
ଗୋଟେ
ଆସିପାରନ୍ତି
କଥା
ବୋଧେ
ବୁଝିବାର ଥିଲା ଆମର
କନେକ୍ସନ
ଯୋଉ
ଯଦି
ଡିସେମ୍ବର ଏକ୍ଜାମ ହବ ତା ପାଇଁ ତ ରେଜିଷ୍ଟ୍ରେସନ ଆରମ୍ଭ ହେଇନି
ନା ନା
ନାଇଁ
ୱାନ୍ସ
ମ୍ୟାଡାମ
ଆପଣ
ସେ
ଆସାଇନମେଣ୍ଟ
ସେପ୍ଟେମ୍ବର
ସବମିଟ
ଫାଷ୍ଟରୁ
କରିବେ
ଆସିବ।
ଆଜ୍ଞା ଆଜ୍ଞା
ଆସାଇନମେଣ୍ଟ
ଆଜ୍ଞା
ସବମିଟ କଲା ପରେ ଆସିବ ସେ ଯାହା କହୁଥିଲେ ସେପ୍ଟେମ୍ବର 30 ରେ ଆପଣ ଆସାଇନମେଣ୍ଟ ସବମିଟ କଲା ପରେ ଆସାଇନମେଣ୍ଟ ସବମିଶନ ଡେଟ୍ ସରିଲା ପରେ ଫର୍ମ ଫିଲଅପ ପାଇଁ ଡେଟ୍ ଅକ୍ଟୋବରରେ ଆସେ ଅକ୍ଟୋବରରେ ଆପଣ ଫର୍ମ ଫିଲଅପ କରିବେ
ନାଇଁ ସାର୍ ସାର୍ ଶୁଣନ୍ତୁ
ଆଜ୍ଞା
ଦିଲ୍ଲୀପ ସାର୍
ହଁ କୁହନ୍ତୁ ସାର୍
ନାଇଁ ମୁଁ ହଁ ଏବେ ଇଗ୍ନୋର ଯୋଉ ଆମର ଆରସି ଅନୁଗୁଳରେ ଦେଖୁଥିଲି ତାଙ୍କର ନୋଟିସ ବି ଦେଇଛନ୍ତି ତାଙ୍କର ସେପ୍ଟେମ୍ବର ଫାଷ୍ଟରୁ ସେପ୍ଟେମ୍ବର ଲାଷ୍ଟ ଯାଏଁ ଅଛି ଫର୍ମ ଫିଲଅପ ହଉଛି ସେମିଷ୍ଟରର
ଆଜ୍ଞା ଆଜ୍ଞା ଆଚ୍ଛା 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 ଆମକୁ ସେ ଓରିଏଣ୍ଟେସନରେ କହିଥିଲି ଯାହା କହିଥିଲି ନା ଆପଣ ସେପ୍ଟେମ୍ବର 30 ସରିଲା ପରେ ଅକ୍ଟୋବରରେ ଆମର ଫର୍ମ ଫିଲଅପ ଟା ହୁଏ ଆଉ ଅକ୍ଟୋବର 30 ରୁ ନଭେମ୍ବର ମାନେ ଟୋଟାଲ ନଭେମ୍ବର ମନ୍ଥରେ ସେମାନେ କହିଲେ କି ଆମେ ଗୋଟେ ମନ୍ଥ ନଉ କେତେ ପିଲା କୋଉଠି ଅଛନ୍ତି କୋଉଠି କେତେ ଆକୋମୋଡେଟ ହେବେ ତା ରିଲେଟେଡ ଆମେ ପ୍ରୋଗ୍ରାମିଂ କରିବା ପାଇଁ ଟୋଟାଲ ନଭେମ୍ବର ମନ୍ଥଟା ଆମ ହାତରେ ରଖୁ ତ ନଭେମ୍ବର ପୂର୍ବରୁ ଆମେ ଫର୍ମ ଫିଲଅପ କରୁ ଡିସେମ୍ବରରେ ଏକ୍ଜାମ ଟା ଷ୍ଟାର୍ଟ କରୁ ତ ଆପଣ ଯାହା କହୁଛନ୍ତି ସେମିତି ବି କରିପାରନ୍ତି ସେପ୍ଟେମ୍ବରରେ ବି ଆମର ବି ଦେଇପାରନ୍ତି ବିଫୋର
ହଁ ସାର୍
ଆସାଇନମେଣ୍ଟ
ମୁଁ
ସବମିଶନ ବି
ଦେଖିଥିଲି
ଦେଇପାରନ୍ତି ଆଜ୍ଞା
ନାଇଁ ଆରସି
ହ୍ୟାଲୋ
ଅନୁଗୁଳର ଦେଖୁଥିଲି ଆଜି ନୋଟିସ ଦେଖିଥିଲି ଯେ
ହ୍ୟାଲୋ
ଜଣା ପଡିଲା ଯେ ସେ 30
ଆଜ୍ଞା ଆଜ୍ଞା
ସେପ୍ଟେମ୍ବର
ଆଚ୍ଛା
ଅଛି।
ଆଚ୍ଛା ମେ ବି ଆମର ବି ସେପ୍ଟେମ୍ବରରେ
ହ୍ୟାଲୋ
ଦେଇପାରନ୍ତି
ସାର୍ ହ୍ୟାଲୋ ଦିଲ୍ଲୀପ ସାର୍ ହ୍ୟାଲୋ
ଆଜ୍ଞା ମ୍ୟାଡ଼ାମ କୁହନ୍ତୁ
ଆଜ୍ଞା ନାଇଁ ମୁଁ ଏଇ ଯୋଉ କହୁଥିଲି କଣ କି ଆମର କୋଉଟା କହୁଥିଲି ଭୁଲିଗଲି
ଆମର କେନ୍ଦ୍ରାପଡା ପିଲା କିଏ ଅଛନ୍ତି ଏମିତି
ଆଜ୍ଞା ଆଜ୍ଞା ମ୍ୟାଡ଼ାମ ମୋର କେନ୍ଦ୍ରାପଡ଼ା ଏ ଯୋଉ
ଆପଣଙ୍କର
କଲେଜ
ତ
ଆମର
ମ୍ୟାଡାମ କଲେଜ
ଏନ୍ଓସି ପାଇଁ
ପାଖରେ ରହିଲେ
ହ୍ୟାଲୋ
ତ
ସାର୍ ଏ
ହ୍ୟାଲୋ
ଯୋଉ ଏନ୍ଓସି
ହଁ
ପାଇଁ
କୁହନ୍ତୁ
ହ୍ୟାଲୋ
କୁହନ୍ତୁ
ଆମର ଯୋଉ
ଆଜ୍ଞା
ପରମିସନ ଆଣିବା ପାଇଁ ଆମର ତ ଯୋଉ
ଆଜ୍ଞା
ବିଏଡ୍ ଫେଡ୍
ଦିଲ୍ଲୀପ ସାର୍
ସେମିତି
ନମ୍ବରଟା ଟିକେ ଦେବେ
ଦେଇଥିଲେ
କି?
ମାନେ କିଛି ହ୍ୟାଲୋ ସାର୍ ଶୁଣୁଛନ୍ତି
ହଁ କହୁନାହାନ୍ତି
ଆଜ୍ଞା ନାଇଁ ମୁଁ କହୁଥିଲି ଆମର ଯୋଉ ପରମିସନ ପାଇଁ ଯୋଉ ଡିଓ ଅଫିସରେ ଯୋଉ ଆମେ ଆଣିବା ତେଣୁକରି ସେମାନେ ଆଗରୁ ସେମିତି ଦେଇ ଦେଉଥିଲେ ଏବେ କହୁଛନ୍ତି ଯେହେତୁ ପ୍ରାକ୍ଟିକାଲ ସବଜେକ୍ଟ ତୁମର ଅଛି ତେଣୁକରି ତୁମେ ଇଗ୍ନୋ ଅଫିସରୁ ଆର୍ସିରୁ ଗୋଟେ ଲେଖା ନେଇକି ଆସନ୍ତି ଆମେ ମାସ ପାଇଁ ଯେଉଁ ପ୍ରାକ୍ଟିକାଲ କରିବୁ ଆମର କିଛି ହାମ୍ପର ହେବନି ତେଣୁ ଏଇଟା ସବୁ ଡିଷ୍ଟ୍ରିକ୍ଟରେ
ମ୍ୟାଡ଼ାମ
ଚାଲିଛି ନା
ଶୁଣନ୍ତୁ
ଆପଣ ମ୍ୟାଡାମ
ମ୍ୟାଡ଼ାମ
ଫର୍ମ ଆପ୍ଲାଏ କଲା ବେଳେ ପରମିସନ ଆଣିନାହାନ୍ତି କି?
ନାଇଁ ନାଇଁ ଯେତେବେଳେ ମୁଁ ଯୋଉ ଆଡମିସନ କଲି ସେତେବେଳେ ନେଇକି ଯାଇଥିଲି ଅଫିସକୁ ମାନେ ପରମିସନ ପାଇଁ। ସେତେବେଳକୁ ସେ ଡାଏରୀ କରିକି ରଖିଲେ। ତାପରେ ଆର୍ଟ୍ସ ପିଲାଙ୍କୁ ଦେଇଦେଲେ ଏବେ ଯୋଉମାନଙ୍କର ଆର୍ଟ୍ସ ସବଜେକ୍ଟ ହେଲା କି
ଆଚ୍ଛା ତ
ବୁଝିପାରିଲେ
ମ୍ୟାଡ଼ାମ
ମ୍ୟାଡାମ?
ଶୁଣନ୍ତୁ ମୁଁ ମ୍ୟାଡ଼ାମ ଗଭର୍ଣ୍ଣମେଣ୍ଟରେ ନାହିଁ ଯେହେତୁ ମୁଁ ପ୍ରାଇଭେଟ ଇନଷ୍ଟିଟ୍ୟୁସନରେ ଅଛି ମୁଁ କହିପାରିବିନି ମ୍ୟାଡ଼ାମ ଆପଣଙ୍କ ପ୍ରୋସେସ କଣ ତେଣୁ ଯିଏ
ଆଜ୍ଞା
ଅଛନ୍ତି
ଆଜ୍ଞା
ଗଭର୍ଣ୍ଣମେଣ୍ଟ
ନାଇଁ
ମ୍ୟାଡ଼ାମ ଅଛନ୍ତି
ହଉ
ସେମାନେ
ହଉ
କହିପାରିବେ।
ନାଇଁ ନାଇଁ ମୋର ଏଟା
ମ୍ୟାଡାମ
ଅଲଗା
ଶୁଣନ୍ତୁ ଆପଣ ଗୋଟେ ଭୁଲ କରିଦେଲେ ସେ ଏଇଖିଣା ସେ ଟିକେ ଦବା ପାଇଁ ଇଏ କରିବେ। ଆପଣ ଯେତେବେଳେ ଆପ୍ଲାଏ କଲେ ସେ ଡେଟ୍ ରୁ ପ୍ରାୟ ନେଇ ଆସିଥାନ୍ତେ ଆପ୍ଲାଏ ଆଣ୍ଡ ଆପିୟର ଅଲ୍ ଦ ଏକ୍ସାମିନେସନ ଆପଣଙ୍କୁ ଆଉ କିଛି ଅସୁବିଧା ହେଇନଥାନ୍ତା। ମୁଁ ନେଇ ଆସିଛି ସେଇଥିପାଇଁ।
ନା ସେତେବେଳେ ମ୍ୟାଡାମ ମୁଁ ଜାଣିଥିଲି ଆମେ ତ ବିଏଡ୍ ବେଳେ ବି ଯେହେତୁ ସେତେବେଳେ ସେ ପ୍ରାକ୍ଟିକାଲ ସବଜେକ୍ଟ
ସେଇଟା
ରହୁଛି ନା।
ଏବେ ସେମାନେ ଟିକେ ଇଏ କରିବେ ଆଉ।
ଆଉ ତେଣୁ
ଦେଖନ୍ତୁ
କରି ଆଜ୍ଞା ଅଫିସ ଯିବାକୁ ପଡିବ ନାଇଁ?
ହଁ ହଁ।
ମତେ ଟିକେ
ଅଫିସ
କହିବେ କି
ସେଠୁ
ଡିସ୍କସନ ଟପିକ ଟା କଣ ମୁଁ ଜାଣିପାରୁନି।
ତାଙ୍କୁ
ଅଫଲାଇନ
ଗୋଟେ
ଥିଲା।
ମ୍ୟାଡାମ ଆପ୍ଲିକେସନ ନେଇକି ତାଙ୍କୁ ଇଏ କରିବାକୁ ପଡିବ ନା କଣ କେମିତି?
ହଁ ହଁ ଆପଣ ଆପ୍ଲିକେସନ ଦେବେ ଆପଣଙ୍କ ଏଚଏମ୍ ଗୋଟେ ଫରୱାର୍ଡିଂ ଦେବେ ତା ସହିତ ଆପଣ ଯୋଉ ଆଡମିସନ କରୁଛନ୍ତି ତାର ପ୍ରୋସପେକ୍ଟସ ର ଫାଷ୍ଟ ଫ୍ରଣ୍ଟ ପେଜ ଜେରକ୍ସ ଦେବେ। ଦେଲେ ପରେ ଆପଣଙ୍କର ଅଫିସ ମାନେ ଚିଠି ଗଲା ଆପଣଙ୍କର ଡି ଅଫିସ ହଉ କି ଯେକୌଣସି ଅଫିସ ହଉ ତ ସେମାନେ ଗୋଟେ ଫରୱାର୍ଡିଂ ଲେଟର ଦେବେ। ସେମାନେ ଲେଟର ପକେଇକି ଗୋଟେ ମେମୋ ନମ୍ବର ଦେଇ ନେବେ ଯୋଉ ନମ୍ବର ଟା ଆପଣଙ୍କୁ ଇନ ଫ୍ୟୁଚର ହେଲ୍ପ କରିବ।
ନାଇଁ ନାଇଁ ସେ ଯୋଉ ଡିଓ ବାଲା ସେମାନେ କହୁଛନ୍ତି ତୁମେ ଆଗେ ଯେତେବେଳେ ଆଡମିସନ ହେଇଛି ଆପଣ ସେଠୁ ଆଗେ ଗୋଟେ ଆଣନ୍ତୁ ଯେ ପ୍ରାକ୍ଟିକାଲ ପାଇଁ। ମାନେ ସେ କହୁଛନ୍ତି ଆମେ ସେଟାକୁ ଆଣିଲେ ଆମେ ତମକୁ ପରମିସନ ଦେବୁ। ସେ ଆମର ଯୋଉ ଡିଓ ଅଫିସରେ।
ମ୍ୟାଡାମ ସେତେବେଳେ ଟିକେ ଥିଲା ସେତେବେଳେ ଡିଓ ମ୍ୟାଡାମ ଥିଲେ ଏପଟେ ଚେଞ୍ଜ ହେଇଛନ୍ତି। ତ
ଆଜ୍ଞା
ସମସ୍ତଙ୍କୁ କଣ କେମିତି ହବ ଆଉ।
ଆପଣ କଣ ମ୍ୟାଡାମ କେନ୍ଦ୍ରାପଡା?
ଆଜ୍ଞା।
ଓହୋ ଏବେ ତ ଡିଓ ଚେଞ୍ଜ
ମ୍ୟାଡ଼ାମ
ହେଇଛନ୍ତି ନା?
ତାହେଲେ ମୁଁ ଲେଫ୍ଟ ହେଇଯାଉଛି ଟିକେ
ହଁ
କାମ
ହଁ ହଁ ଆପଣ
ଅଛି
ଯଦି ଇଏ
କରିଦେବି।
ତାହେଲେ ଆପଣ ଆଗରୁ ମ୍ୟାଡ଼ାମ ନେଇ ଆସିଛନ୍ତି ନାଇଁ?
ଆଜ୍ଞା।
ଓହୋ ଆଜ୍ଞା ଆଜ୍ଞା।
ପୁରୀର କିଏ ଅଛନ୍ତି ନମ୍ବର ଟିକେ ଦେବେ କାହାର?
ମ୍ୟାଡାମ ନାଁ ଟା କଣ କହିଲେ ଆପଣଙ୍କର? ହ୍ୟାଲୋ।
ହ୍ୟାଲୋ। ହ୍ୟାଲୋ ପୁରୀ କି ଭୁବନେଶ୍ୱରରୁ କିଏ ଅଛନ୍ତି କି? ହ୍ୟାଲୋ। 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 ହ୍ୟାଲୋ ହ୍ୟାଲୋ।